Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the fascinating science of hidden planets. Worlds that may exist all around the galaxy, yet remain almost completely beyond our sight. For centuries, we thought that planets were rare, and the only ones we knew of were in our very own solar system. But now, we know that planets are everywhere, and are far more common than we ever imagined. And the truly extraordinary part is that the worlds we've already found may only represent a tiny fraction of what's really out there. Some planets are so difficult to detect that astronomers can spend years searching for even the faintest piece of evidence. Others may never reveal themselves directly, and we can only infer their existence through subtle clues or unexplained observations. And that raises a fascinating possibility. The galaxy could be filled with entire worlds that nobody has ever seen. Some may be closer than we realize. Others may belong to planetary systems whose true size is still unknown. And every new discovery has the potential to change what we think a planetary system can actually be. Tonight, we'll explore what may be hiding beyond the planets we already know, and how scientists are slowly uncovering a much bigger universe of worlds. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to loosen its grip on the day, join me as we explore these hidden worlds together. Let's begin. Most planets in our galaxy may wander through space without stars. Astronomers call them rogue planets because they travel through the galaxy without orbiting a sun. Some may have formed inside ordinary planetary systems before gravitational encounters threw them into interstellar space. Others may have collapsed directly from small clouds of gas and never belonged to a star at all. Finding them is extraordinarily difficult because planets normally become noticeable by reflecting light from their suns. A rogue world has no nearby star to illuminate it. Once its youthful heat fades, it can become almost completely dark. That means the Milky Way could contain an immense population of worlds that ordinary telescopes simply overlook. The strongest clues come from gravitational microlensing, which can reveal an invisible object when it passes between Earth and a distant star. Surveys have already uncovered candidates with planetary masses. The remarkable possibility is that the familiar picture of planets circling stars may represent only part of the story. A huge fraction of the galaxy's worlds could be traveling alone between them. Thousands of planets have been discovered, yet most remain completely unseen. When astronomers announce a new planet, they usually have not photographed a recognizable world floating beside its star. The distances involved are simply too great. Even nearby planetary systems appear compressed into tiny points of light. The problem becomes harder because a star can outshine an orbiting planet by millions or billions of times. Instead, astronomers often discover planets by measuring what those worlds do to something easier to observe. A planet might slightly dim its star during an orbit. It might tug the star backward and forward through gravity. In other cases, its presence can alter the timing of another object. These measurements create a remarkable situation in modern astronomy. Scientists can calculate a planet's mass, orbit, temperature, or approximate size without ever resolving its surface as a separate object. The planet becomes known through consequences rather than appearance. It is rather like discovering an unseen dancer by watching the floorboards move beneath their feet. Thousands of distant worlds entered our catalogues through evidence this indirect. Some hidden worlds reveal themselves only by bending another star's light. Gravity does more than control orbits. According to general relativity, mass also bends the path taken by light. If a hidden planet passes almost perfectly between Earth and a distant background star, its gravity can distort the star's light on the way to us. The effect is called gravitational microlensing. Nothing needs to shine from the planet itself. The world can be cold, dark, and otherwise impossible to detect. During the alignment, the background star briefly appears brighter because the planet's gravity redirects additional light toward Earth. The effect can be extremely subtle and may last only a short time. Astronomers therefore monitor huge numbers of stars and wait for the rare occasions when geometry cooperates. A planetary lens may be separated from its own star, or may travel completely alone. Either way, gravity announces its presence. This gives astronomers something almost magical in scientific terms. An object that emits virtually no detectable light can still reveal itself because empty-looking space around it is not behaving quite normally. Entire planetary systems could exist where our usual searches would miss everything. Every planet hunting technique has its own blind spots. Transit surveys work best when planets cross directly in front of their stars from our viewpoint. Radial velocity searches favor worlds that produce measurable gravitational motion. Direct imaging performs best when a planet is bright enough and sits far enough from its star to be separated from the glare. A planetary system can therefore be real, nearby, and completely undetected simply because its architecture is inconvenient for our instruments. Imagine a system filled with small worlds whose orbits never cross the face of their star from Earth. If those planets are lightweight and widely spaced, they may produce only weak gravitational signals as well. Nothing about that system would make it unusual in nature. It would merely be difficult for us to notice. This is one reason astronomers treat the known exoplanet population cautiously. The catalogue is not a complete map of what exists. It is partly a map of what our current methods happen to be good at finding. Rogue planets may outnumber worlds that remain bound to stars. Counting starless planets is one of astronomy's hardest statistical problems. A normal planet can be searched for repeatedly because astronomers know where its parent star is. A rogue world offers no such fixed address. It may cross a useful line of sight once and then continue through the galaxy unseen. Microlensing surveys have nevertheless detected enough short events to suggest that free-floating planetary bodies could be extremely numerous. Exactly how numerous remains uncertain. Different surveys have produced different estimates because the smallest objects create the briefest signals and are easiest to miss. Even so, the possibility is extraordinary. Planet formation may produce far more worlds than the orderly systems around visible stars would suggest. Some young systems probably lose planets during unstable gravitational rearrangements. Other planetary mass objects may form separately from stars. If both processes are common, the space between stellar systems is not truly empty in a planetary sense. It may contain a vast hidden population that we have only begun to sample through rare flashes of gravitational evidence. Earth-sized planets could be drifting alone through the Milky Way right now. A planet does not need Jupiter's enormous mass to survive after losing its star. In principle, a rocky world comparable to Earth could be expelled from a young planetary system and continue orbiting the galaxy independently. Detecting one is difficult because a small planet creates a weaker gravitational lens than a giant world. Its microlensing event may last only hours instead of days. That short window forces surveys to observe crowded star fields repeatedly and with exceptional precision. Candidate events have shown that objects with roughly terrestrial planetary masses can exist without obvious host stars nearby. Such a world would be radically different from Earth despite having a familiar mass. Its surface would receive no steady daylight from a sun. Any residual warmth would have to come from its interior or from an insulating atmosphere. From a distance, it would be almost impossible to distinguish from the darkness around it. Yet gravity would still travel outward from the planet and briefly announce its existence whenever the alignment with a background star became just right. A distant planet can betray itself by making its star gently wobble. Stars look dominant in planetary systems, but they do not remain perfectly fixed while planets circle them. Both objects orbit their shared center of mass. When a large planet travels around a star, the star performs a much smaller motion in response. Astronomers detect this through the Doppler effect. As the star moves slightly toward Earth, its spectral lines shift toward shorter wavelengths. When it moves away, those same lines shift toward longer wavelengths. Repeated shifts can reveal a regular pattern caused by an unseen companion. This technique is called the radial velocity method. It has uncovered planets that never pass in front of their stars and cannot be photographed directly. The measurements can also provide an estimate of the planet's minimum mass and orbital period. Modern instruments can detect stellar motions measured in only a few meters per second. That means the gravitational pull of a planet far too faint to see can still move an entire star enough for astronomers on Earth to notice the rhythm. Planets resembling Jupiter may hide for decades between each journey around their stars. A planet's year becomes longer as its orbit grows wider. Jupiter needs nearly 12 Earth years to circle the Sun once. Move a similar planet farther outward and a complete orbit can take several decades. That creates a practical problem for astronomers. To recognize an orbit confidently, they often need to observe a substantial fraction of its repeating pattern. A telescope program lasting a few years may therefore catch only a slow curve in the star's motion rather than the complete signature of a planet. Such worlds can remain listed as uncertain companions for years, while fresh measurements gradually fill in the missing arc. The situation becomes especially challenging for planets around stars that were not monitored consistently in the past. Long-period giants are scientifically valuable because they may resemble the outer architecture of our own solar system more closely than the hot giants found close to other stars. Yet their leisurely motion makes them stubborn targets. Astronomy sometimes advances not through faster measurements, but through researchers patiently waiting for a distant year to unfold. Some undiscovered worlds could orbit farther from their stars than Neptune does. Neptune circles the Sun at roughly 30 times Earth's distance. Exoplanets can occupy even wider paths, but such worlds are easy to miss. A distant orbit produces few transits during a human observing campaign. The planet also pulls on its star more slowly, stretching the gravitational signal across many years. If the world is cold, it emits little infrared radiation and reflects only a small amount of starlight. These difficulties create a poorly explored region around other stars. Astronomers know far more about planets that crowd close to their suns than they do about remote planetary outskirts. Yet those outer regions could hold important clues about how systems develop. Giant planets can migrate after formation. Smaller bodies can be scattered outward. Some worlds may settle into extraordinarily broad orbits after complex encounters with other planets. Consequently, a distant star that appears to have only a few inner planets may possess an outer realm we have never detected. Its planetary system could extend far beyond the boundary that current observations make obvious. Our own solar system may still conceal a large planet beyond Neptune. The idea known as Planet 9 emerged from an intriguing pattern among several small bodies in the distant solar system. Some of their elongated orbits appear clustered in ways that researchers have argued might be explained by the gravity of an unseen planet. In many versions of the hypothesis, this world would have several times Earth's mass and travel far beyond Neptune on an enormous orbit. It would not resemble a secret planet hiding just beyond Pluto. It could spend most of its time hundreds of times farther from the Sun than Earth does. At such distances, sunlight would be extremely weak. Even a substantial planet could appear as a faint moving point against an immense background of stars. The hypothesis remains unconfirmed. Other explanations for the unusual orbital pattern have been proposed, including observational bias within the small sample of known objects. Searches continue because either outcome would be fascinating. Finding the planet would transform the map of our solar system. Failing to find it would force astronomers to explain the distant orbits another way. Most known exoplanets were discovered without anyone ever seeing the planets themselves. In astronomy, seeing can mean something very different from forming a picture. A telescope may record the light from a distant star while the planet beside it remains hopelessly buried inside that same point of brightness. Astronomers then search the data for a repeating physical signature. The remarkable part is how much can be reconstructed from those signatures. Orbital periods reveal how quickly worlds circle their suns. Transit depths can indicate planetary sizes. Gravitational measurements can constrain masses. Combining different methods can even reveal density, which helps distinguish rocky planets from gas-rich ones. This form of discovery has turned tiny changes in light into a census of completely inaccessible places. Only a small fraction of exoplanets have been directly imaged as separate points from their stars. For nearly all the rest, the planet exists in our knowledge because the measurements fit a consistent physical model. The result is one of modern astronomy's strangest achievements. Humanity has built a catalogue containing thousands of worlds that no human eye has ever actually viewed as worlds. A planet passing before its star can dim the starlight slightly. Imagine watching a distant star while an orbiting planet crosses directly between the star and Earth. The planet blocks a tiny portion of the stellar disk and causes the measured brightness to fall. After the planet moves away, the brightness returns to normal. If the same dip repeats at regular intervals, astronomers may have found a transit. The depth of that dimming provides a clue to the planet's size compared with its star. A giant planet can produce a noticeable reduction. An Earth-sized world crossing a sun-like star blocks only about 1/10,000th of its light. Detecting such a minute change requires exceptional stability and many careful measurements. Transit searches became enormously productive because one telescope can monitor thousands of stars at the same time. A single field of view can therefore contain many opportunities for discovery. What looks visually like an unchanging collection of stars becomes a landscape of tiny repeating eclipses. Each reliable dip can mark a world completing another orbit around a sun that may be hundreds or thousands of light-years away. Orbital geometry prevents most distant planets from ever producing visible transits. For a transit to occur from Earth's perspective, a planet's orbit must be aligned with remarkable precision. The planet can circle its star perfectly well forever without ever crossing the stellar disk as we see it. Tilt the orbital plane by only a modest amount, and the world passes above or below the star instead. The likelihood of a transit becomes smaller for planets on wider orbits because the necessary alignment is narrower. This means transit surveys are wonderfully productive but fundamentally selective. They do not show us every planet around the stars being observed. They show us the subsec whose orbital planes happen to point in useful directions. Astronomers correct for this bias when estimating how common different kinds of planets are. If one transiting world is detected, many similar systems may exist with orientations that make their planets invisible to that method. The night sky therefore contains a geometrical hiding trick on an enormous scale. Countless planets may be circling stars we monitor closely while never passing across them from our particular location in the galaxy. Even a perfectly Earth-like world could remain invisible from the wrong angle. Suppose another planetary system contained a planet with Earth's size and an orbit very much like ours. That does not guarantee we could detect it. If its orbital plane were tilted away from our line of sight, the planet would never produce the familiar yearly transit astronomers hope to measure. Its gravitational influence on a sun-like star would also be extremely small. Earth moves the sun around their common center of mass, but the resulting stellar motion is only a tiny fraction of the signals produced by massive, close-orbiting planets. Direct photography would face another obstacle. A pale, rocky planet beside a bright star would be extraordinarily faint and separated from it by a minuscule angle when viewed across interstellar distances. In other words, an almost perfect Earth analog could exist around a nearby star, while several major search techniques struggle to reveal it. This is an important reminder when we look at systems that appear empty. An absence of detected planets does not necessarily mean an absence of planets. Sometimes the architecture simply refuses to cooperate with our viewpoint. Tiny changes in starlight can reveal planets thousands of light years away. Planet hunting often depends on measuring differences in brightness that a human eye would never notice. Space telescopes can record stellar light repeatedly and compare one measurement with the next. If the data show a shallow dip that returns with the same timing, the pattern may reveal a planet far beyond anything we could visit. The precision involved is astonishing. Astronomers must separate genuine planetary signals from instrument noise and changes occurring on the star itself. Sunspots, stellar pulsations, and nearby stars can all complicate the measurement. Yet carefully calibrated observations allow researchers to identify remarkably small variations across enormous distances. This is how surveys have turned parts of the sky containing ordinary-looking points of light into maps of planetary systems. Distance does eventually make the task harder because faint stars provide fewer photons to measure. Even so, planets are being found around stars thousands of light years away. Their existence reaches us not as a visible globe, but as a tiny missing fraction of light recorded by an exquisitely sensitive detector. Gravity can uncover planets too dark for any telescope to photograph directly. Light is not the only messenger available to astronomers. Every planet possesses mass, and mass influences the motion of other objects around it. That makes gravity a powerful way to investigate worlds that produce almost no detectable light of their own. A cold planet in a remote orbit may be invisible in an ordinary image. Yet its pull can shift the position of its star or disturb another body in the same system. In some circumstances, gravity can even affect light traveling from an unrelated object much farther away. The key advantage is that darkness does not weaken gravitational influence in the way it weakens photography. A planet can be black against the sky and still exert exactly the pull expected from its mass. Astronomers exploit this by looking for motions and alignments that visible objects alone cannot explain. The result changes what the word hidden means. A planet can escape our cameras completely while remaining detectable through the shape of an orbit or the motion of a star. Gravity gives invisible worlds a way to leave evidence. Micro-lensing discoveries depend on rare alignments that may never happen again. Most planet detection techniques reward patience because the signal repeats. A transiting planet comes around again. A star pulled by a companion continues its gravitational cycle. Microlensing can be very different. The event depends on a foreground object passing extremely close to our line of sight toward a more distant star. Earth, the lensing system, and the background source are all moving through space. Once that alignment breaks, it usually does not return. Astronomers may therefore get only one chance to capture the event properly. Follow-up observations can study the area afterward, but the distinctive magnification itself is gone. This makes microlensing astronomy unusually dependent on rapid monitoring and cooperation between observatories. An unexpected brightening can begin while one part of Earth is in daylight, then continue as telescopes elsewhere take over. The final light curve records a fleeting geometry that may never be recreated. Hidden planets discovered this way can enter human knowledge through a single encounter lasting days or hours. Miss that brief alignment and the world may continue through the galaxy unnoticed. A hidden planet can briefly turn gravity into a natural magnifying glass. When a foreground star passes near the line of sight to a much more distant star, the foreground star's gravity can magnify the background light. If the foreground star has a planet, that planet creates an additional gravitational disturbance of its own. Instead of producing a simple, smooth brightening, the event can develop a small extra feature. Astronomers call the most dramatic structures caustics. Crossing one can cause the background star to brighten sharply for a short period. The shape and duration of that anomaly can reveal the presence of the planet and provide information about its mass relative to the star. In effect, nature builds an enormous lens from gravity itself. No glass is involved. No telescope created the magnification. The geometry of space supplies it. This technique is especially valuable because it can detect planets at distances from their stars that other searches often undersample. A planet that would otherwise contribute no visible light can briefly alter a cosmic magnifying event enough to expose itself to observers across Earth. Some planetary discoveries begin with a star becoming unexpectedly brighter. A sudden increase in brightness usually sounds like something happening to the star itself. Perhaps it flared or changed internally. In microlensing surveys, however, a star can brighten because an unseen object has moved through the foreground. Automated programs watch dense stellar fields and flag these unusual increases as they occur. Most events are caused by stars or other massive objects acting as gravitational lenses. A small fraction show additional distortions that reveal planets. The discovery process therefore begins backwards compared with a transit. Astronomers are not searching for missing light. They are searching for extra light that arrives because gravity has redirected it. Researchers then compare the observed brightening with detailed lensing models. A smooth curve may indicate a single lens. A kink or short-lived spike can suggest a more complicated system. From an otherwise anonymous star that became brighter for a while, scientists can infer the existence of a planet in the foreground. The distant star is not the planetary host at all. It simply serves as the background light source that makes the hidden system detectable. Gaia found a giant planet by measuring its star's tiny motion. The Gaia spacecraft was built to measure stellar positions with extraordinary precision. As it repeatedly surveys the sky, it tracks how stars move across years. Most of that motion comes from their journey through the galaxy and from Earth's changing viewpoint during Gaia's orbit around the Sun. Sometimes a star also traces a tiny additional loop. That motion can be caused by an unseen companion pulling the star around their common center of mass. This technique is called astrometry. It differs from radial velocity because astronomers measure movement across the sky rather than motion toward or away from Earth. Gaia's precision has allowed giant planetary companions to emerge from these minute positional shifts. Astrometry is particularly valuable for wider orbits where other detection methods may struggle. It can also reveal the true tilt of an orbit, which helps astronomers determine a companion's actual mass rather than only a minimum estimate. A planet that contributes essentially no useful light can therefore reveal itself through a microscopic change in where its star appears against the distant background. Gaia 23 Bra b hides nearly 40,000 light-years from Earth. This giant world demonstrates how far beyond their intended limits planet-hunting missions can sometimes reach. The system first drew attention when the Gaia spacecraft detected an unusual brightening in 2023. Gaia had caught a gravitational microlensing event, but its observations alone were not frequent enough to reveal the planet clearly. Researchers later searched archived observations from NASA TESS spacecraft. Remarkably, TESS had been watching the same region during the event. Its measurements recorded extra features caused by the planet. The resulting analysis revealed a world roughly 1.5 times Jupiter's mass, orbiting an orange dwarf star. Its distance is extraordinary because TESS normally discovers planets much closer to Earth, through transits. This one lies on the opposite side of a huge portion of the Milky Way. Nobody designed TESS primarily to find such remote microlensing planets. The discovery only became possible when researchers returned to observations already sitting in an archive and asked a completely different question. It suggests other extraordinary worlds could already be recorded in existing data without anyone recognizing them yet. Archived telescope observations can contain planets nobody noticed the first time. A telescope does not necessarily reveal everything hidden in its observations when those observations are first collected. Space missions gather enormous streams of measurements, and researchers usually process them with particular goals in mind. Years later, somebody can return with a new technique and discover that the data contain a signal nobody originally searched for. This has become an important part of exoplanet astronomy. Improved software can remove noise more effectively. New physical models can recognize patterns that once looked meaningless. Discoveries made elsewhere can also tell astronomers exactly where to search old observations again. In some cases, a faint planetary signature was always present, but remained buried beneath stellar variability or instrumental effects. The telescope does not need to revisit the sky because the photons were already captured. What changes is our ability to understand them. Astronomical archives therefore behave almost like unexplored observatories frozen in time. A spacecraft that completed its observation years ago can effectively make a new discovery today. Some hidden planets may already exist inside humanity's stored measurements and simply await the right analysis. Old data sometimes reveals worlds using methods the telescope never originally intended. Space telescopes are usually designed around carefully defined scientific missions. Their cameras, observing schedules, and software are optimized for particular measurements. Yet nature does not always cooperate with those categories. A telescope built to detect planets passing across stars may accidentally record a gravitational event instead. An instrument designed to study stellar brightness might capture evidence of an unexpected planetary eclipse. Once scientists understand that a different signal could be present, they can search the archive again. This can transform an accidental observation into an entirely new use for the spacecraft. The advantage is enormous because building and launching another telescope is extraordinarily difficult. Reinterpreting existing observations allows researchers to gain fresh science without leaving Earth. It also means the value of a mission can continue growing long after its designers imagined its original experiments. Modern astronomy increasingly treats old data as something active rather than finished. Every improvement in analysis creates another chance to discover what was overlooked. A hidden planet can therefore remain unnoticed, not because the telescope failed to record it, but because nobody yet knew the right question to ask. Stars can wobble because unseen planets repeatedly pull them off balance. Imagine a star with several planets around it. Each world pulls gravitationally on the star at every moment, and those competing forces prevent the star from following a perfectly simple path. A massive planet can create a large, rhythmic motion. Smaller companions add subtler movements on top of it. When astronomers monitor the star for long enough, these overlapping patterns can sometimes be separated into individual planetary signatures. The process resembles hearing several musical notes blended into a single sound and working backward to identify each instrument. This has allowed researchers to uncover systems containing multiple worlds without seeing any of those planets directly. The challenge increases when orbital periods are similar or when stellar activity creates signals of its own. Yet repeated observations gradually expose the underlying rhythms. A star that appears stationary to the eye may actually be performing a complicated gravitational dance spanning days, years, or decades. Every hidden companion contributes something to that movement. By measuring the combined wobble precisely enough, astronomers can reconstruct an unseen planetary system from the motion of the single point of light at its center. Bigger planets usually produce stronger stellar wobbles and easier gravitational clues. Gravity makes massive planets unusually conspicuous, even when their surfaces remain completely invisible. A Jupiter-sized world contains far more mass than Earth, so it pulls much more strongly on its host star. If it also orbits close to that star, the resulting motion can become especially pronounced. This is one reason many of the earliest exoplanets discovered around ordinary stars were giant worlds on surprisingly tight orbits. They were not necessarily the most common planets in the galaxy. They were simply among the easiest for early instruments to detect. The history of exoplanet discovery was therefore shaped by sensitivity. At first, astronomers found the loudest gravitational signals. As instruments improved, smaller movements became measurable and less massive planets began appearing in the catalogues. This progression taught researchers an important lesson about hidden populations. The worlds discovered first are not automatically representative of the worlds that exist most often. Our picture changes as our hearing improves. Giant planets effectively shout through gravity. Smaller planets whisper. Much of modern planet hunting is the attempt to make instruments sensitive enough to hear those quieter companions. Long planetary orbits can require years of observations before their patterns appear. A suspicious signal is not automatically a planet. Astronomers want to see enough of an orbit to understand whether a repeating physical pattern really exists. That becomes frustrating when the suspected world takes 20 or 30 years to circle its star. Researchers may begin observing while they are students and still be following the same signal decades later. During the early years, the star might simply seem to drift gradually in one direction. Only after more measurements arrive does the curve begin to turn and reveal the shape expected from an orbiting companion. Instruments can change during that interval. Observatories can close. Different research teams may inherit the measurements. Combining those generations of data requires careful calibration, because every instrument has its own characteristics. Yet the reward is access to worlds that short surveys barely notice. Long-term planet hunting shows how strangely human timescales interact with astronomy. Some discoveries cannot be rushed by better computing or larger telescopes. The planet itself sets the schedule. To understand its orbit, scientists may simply have to keep watching while years of their own lives pass. Some planets take centuries to complete a single journey around their stars. Move a planet far enough from its sun and its year can become longer than a human lifetime. A world on an extremely broad orbit travels more slowly because its star's gravitational influence weakens with distance. Such planets present astronomers with an unusual puzzle. Nobody can wait several centuries to watch a complete revolution. Instead, researchers observe a tiny piece of the orbit and combine that motion with physics. Direct images taken years apart can show the planet changing position. Measurements of the host star can provide additional constraints. Computer models then test which possible orbits could produce the observed arc. The uncertainty can remain substantial because a short section of a vast ellipse can fit many different trajectories. Nevertheless, even fragments reveal remarkable planetary architectures. Some known companions travel hundreds of times farther from their stars than Earth travels from the Sun. Their orbital periods can extend across generations. A planet discovered today might not return to the same part of its path until people living centuries from now look upward. Hidden worlds can operate on clocks that make an entire human civilization seem brief. Wide-orbit planets are among the easiest worlds for traditional surveys to overlook. Many successful planet searchers naturally favor worlds that remain close to their stars. Close planets transit more frequently, allowing astronomers to confirm repeating dimming quickly. They also tend to produce faster gravitational cycles. A planet on a wide orbit behaves in almost the opposite way. It might cross its star only once during an entire mission. Its gravitational influence unfolds slowly. The greater separation can help direct imaging, but only if the planet is bright enough to detect. This creates a broad region of planetary architecture that remains much less thoroughly explored. The irony is that our own solar system contains several major worlds in this difficult territory. If astronomers observed the Sun from a distant star for only a few years, Jupiter would not provide many opportunities to reveal its full orbital pattern. Saturn would be harder still. This means apparently compact planetary systems may sometimes be incomplete portraits. The inner planets are simply the ones we notice first. Beyond them could lie cold giants following enormous paths that require different techniques and much longer observing campaigns before their presence becomes clear. Cold planets are harder to detect because they emit remarkably little heat. Young planets can remain warm after formation because gravitational contraction and leftover internal energy make them glow strongly in infrared wavelengths. As a planet ages, that stored heat gradually escapes into space. A distant giant that receives little energy from its star can eventually become extremely faint. This matters greatly for direct imaging. Astronomers sometimes block a star's light and search the surrounding region for the infrared glow of orbiting planets. Young, massive worlds are attractive targets because they can still radiate enough heat to stand out. Older, cold planets are far less cooperative. A mature Jupiter analog may be enormously difficult to separate from background noise, even when it sits at a favorable distance from its star. Temperature therefore creates another hidden bias in planetary catalogues. Two planets with similar masses and orbits can have very different detectability simply because one is younger. In effect, astronomers can sometimes see planetary youth more easily than planetary maturity. The oldest cold worlds have had billions of years to fade. They may be common across the galaxy while leaving only exceptionally weak radiation for our telescopes to capture. Darkness makes rogue planets difficult to distinguish from empty interstellar space. A starless world has almost nothing nearby to advertise its location. It produces no regular transit because there is no sun to cross. It creates no repeating stellar wobble because there is no host star being pulled around. If the planet is old, even its own internal warmth may have faded to a weak infrared signal. Against the vast sky, that combination makes detection extraordinarily challenging. Astronomers searching directly for such objects must distinguish faint nearby bodies from distant stars and galaxies that can look similar in individual images. One clue is motion. A nearby rogue planet should slowly shift position against the much more distant background as observations are repeated. Its spectrum and temperature can provide further evidence. Yet the coldest and smallest examples could remain below current detection limits altogether. This means apparently empty space between stars may be populated without looking populated. Darkness is not evidence of absence. It can simply mean there is nothing bright enough to announce what occupies the region. Rogue planets turn interstellar space into one of astronomy's largest potential hiding places for entire worlds. Young giant planets can glow faintly with heat left from their formation. Planet formation releases an enormous amount of energy. Gas and solid material fall together under gravity. Collisions convert motion into heat, and the growing world becomes compressed by its own weight. A newly formed giant planet can therefore remain hot long after the surrounding disk has begun to disappear. For astronomers, this youthful heat provides a precious opportunity. Infrared telescopes can detect radiation coming from the planet itself, rather than relying entirely on reflected starlight. The difference can make direct imaging possible around nearby young stars. These worlds often appear as tiny warm points beside their suns. Measuring their brightness at several wavelengths can reveal clues about temperature, atmospheric clouds, and chemical composition. Over millions of years, however, the planets cool and fade. Their detectability changes with age, even if their mass remains the same. This allows astronomers to study planetary evolution, almost like watching different frames of a very slow film. Young systems show worlds shortly after construction. Older systems reveal the quieter aftermath. The residual heat glowing from youthful giants is one of the few ways planetary formation remains visible after the process itself has ended. Directly photographed exoplanets are usually young giants orbiting far from their stars. Taking a picture of an exoplanet sounds straightforward until scale and brightness are considered. The planet must appear far enough from its star on the sky for the two sources to be separated. At the same time, the planet must produce enough light for instruments to detect it. Young gas giants satisfy both conditions better than most worlds. Their leftover heat makes them bright in infrared wavelengths, while broad orbits place them beyond the worst of their star's glare. This explains why directly imaged planetary systems often look dramatically different from the compact systems found by transit surveys. The detection method is selecting a different part of the planetary population. Famous images can show several giant worlds as distinct points moving around the same star over the years. Watching that orbital movement helps confirm they are genuine companions rather than unrelated background objects. Direct imaging is especially exciting because the planet's own light can be analyzed. Instead of only measuring what a world does to its star, astronomers can begin studying radiation that has actually emerged from the distant planet itself. A star's overwhelming glare can hide a planet billions of times fainter. The difficulty of photographing another Earth is not simply that the planet is small. The nearby star creates an enormous contrast problem. Seen from far away, Earth reflects only a tiny fraction of the sunlight shining beside it. A telescope trying to separate the two is rather like searching for a firefly beside an intensely bright searchlight from an immense distance. Scattered light inside the telescope can spread the star's glare across the exact region where the planet should appear. Small imperfections in mirrors can create patterns that imitate faint companions. Earth's atmosphere adds further distortion for ground-based observatories. Engineers therefore spend extraordinary effort controlling light that they do not want. Mirrors must be exquisitely shaped. Wavefront systems can correct optical errors in real time. Sophisticated processing can remove residual stellar patterns afterward. The challenge illustrates why proximity does not guarantee easy detection. A planet could orbit one of the nearest stars to the Sun and still remain hidden by contrast. Sometimes the greatest obstacle is not distance itself. It is the brilliance of the object standing immediately beside the world we want to see. Coronagraphs reveal hidden planets by suppressing the blinding light of their stars. Astronomers borrowed the name coronagraph from an instrument originally developed to study the Sun's faint outer atmosphere. The basic idea is beautifully simple. Block the bright central source, and fainter surroundings become easier to see. Exoplanet coronagraphs perform a far more demanding version of this trick. Special masks inside a telescope suppress starlight, while allowing light arriving from nearby angles to continue toward the detector. The process must be extraordinarily precise because diffraction causes light to spread around obstacles rather than stopping neatly at an edge. Modern coronagraph designs therefore manipulate the incoming wave of light through several carefully engineered optical stages. When everything works, the region beside a star becomes dramatically darker. A planet that was previously buried inside glare can emerge as a faint point. Researchers can then collect its light for further study. Coronagraphy does not merely make attractive images. It opens the possibility of analyzing atmospheres on worlds that never transit their stars. The technology essentially creates an artificial eclipse inside the telescope so that something unimaginably fainter beside the star has a chance to become visible. Future star shades could block distant suns before their light reaches a telescope. Instead of suppressing starlight inside an observatory, another concept places the blocker thousands of kilometers away in space. A starshade would fly separately from a telescope and position itself precisely along the line of sight to a target star. Its carefully shaped petals would prevent the star's light from entering the telescope, while allowing light from nearby planets to pass around it. The shape matters because a simple circular disk creates diffraction patterns that would spoil the darkness. Engineers designed the petal edges to control those waves and create an extremely deep shadow at the telescope. In principle, the observatory could then search for faint planets close to the hidden star. Changing targets would require the starshade to travel enormous distances across space and realign with exquisite precision, making such missions technically challenging. Yet the scientific prize could be remarkable. A distant rocky world might be photographed as its own point of light. That light could then be separated into a spectrum and searched for atmospheric gases. A giant flower-shaped spacecraft could someday help astronomers examine pale worlds otherwise lost beside their suns. Some planets are discovered through the missing light of their own eclipses. A planet does not always have to cross in front of its star to teach astronomers something. If its orbit carries it behind the star from our viewpoint, the planet itself temporarily disappears. This event is called a secondary eclipse. Before the eclipse, the telescope records light from both objects together. During the eclipse, only the star remains visible. Subtracting those measurements can isolate the tiny contribution that came from the planet. The method works particularly well for hot worlds that emit significant infrared radiation. It can reveal how warm a planet's dayside becomes while facing its star. Measurements at different wavelengths can also provide clues about atmospheric composition and how efficiently heat moves around the globe. Secondary eclipses are extraordinary because the planet may never be separately resolved in an image. Astronomers learn about its radiation by noticing what vanishes when the star hides it. The technique turns disappearance into information. For a few hours, the system becomes slightly dimmer. Inside that almost imperceptible difference lies light that traveled directly from the atmosphere of a world many trillions of kilometers away. Infrared observations can uncover warmth from planets invisible in ordinary visible light. Human eyes evolved to detect a narrow range of wavelengths, but planets radiate energy well beyond that familiar window. Any object warmer than absolute zero emits thermal radiation. For many exoplanets, much of that energy emerges in the infrared. A planet that reflects almost no visible light can therefore remain detectable because of its temperature. Infrared astronomy is especially valuable for studying young giants and intensely heated worlds close to their stars. It can also probe regions hidden behind dust because longer wavelengths penetrate material that blocks visible light more effectively. Observing infrared radiation is technically demanding. Telescopes must often be kept extremely cold so that heat from the instrument itself does not overwhelm the faint celestial signal. Space observatories gain another advantage by operating above Earth's atmosphere, which absorbs significant portions of the infrared spectrum. Once those obstacles are controlled, a seemingly dark planetary system can look completely different. Warm companions emerge where visible images showed nothing. Infrared astronomy reminds us that invisible does not mean absent. It can simply mean that nature is radiating in wavelengths our eyes were never built to perceive. Planetary atmospheres can reveal themselves when starlight filters through their gases. During a planetary transit, most of the star is blocked by the solid or opaque body of the world. A tiny portion of the starlight passes through the edge of its atmosphere before reaching us. Molecules and atoms within that atmosphere absorb particular wavelengths. Astronomers compare the star's spectrum during the transit with measurements taken outside it. The difference can reveal what the planetary air contains. This technique is known as transmission spectroscopy. The signal is astonishingly delicate because the atmosphere forms only a thin ring around an already tiny planetary silhouette. Yet researchers have detected substances such as water vapor, sodium, carbon dioxide, and methane in various exoplanet atmospheres. Clouds can complicate the picture by flattening spectral features, while high-altitude hazes can conceal lower atmospheric layers. Even those obstacles provide information about the world. The planet itself remains unresolved. Nobody sees an atmospheric shell surrounding a globe. Instead, astronomers study the microscopic fraction of stellar light that took a detour through alien air. A distant atmosphere becomes detectable because it leaves a chemical signature on light belonging to another object. Molecules in an atmosphere leave fingerprints even when the planet remains unresolved. Atoms and molecules interact with light at very specific wavelengths because their internal energy levels are quantized. Water absorbs one pattern. Carbon dioxide produces another. Methane leaves a different set of features. These patterns act like fingerprints written into a spectrum. When astronomers spread exoplanet light into its component wavelengths, they search for those characteristic bands. The planet does not need to appear as a detailed disk. In many observations, star and planet remain blended together as a single, unresolved source. Careful techniques separate the planetary contribution mathematically or isolate it during particular orbital phases. The resulting spectrum can reveal chemistry from a place impossibly far away. Interpreting those fingerprints requires caution because temperature, pressure, clouds, and overlapping molecules can change how features appear. Researchers therefore compare observations with detailed atmospheric models instead of simply identifying one line and declaring a substance present. The achievement remains extraordinary. Chemistry once required placing material inside a laboratory. Astronomers can now investigate molecules on worlds they cannot physically see by decoding subtle gaps and peaks in photons that have crossed interstellar space. A planet's changing brightness can reveal which hemisphere faces its star. Astronomers can sometimes follow an exoplanet throughout its orbit and watch the combined light from the system rise and fall. The changing pattern is called a phase curve. Part of the variation comes from seeing different portions of the planet's illuminated side, much as the Moon shows phases from Earth. For hot planets, thermal radiation also changes as hotter and cooler regions rotate into view. By measuring these variations, researchers can infer remarkable details about a world that remains only a point. They can estimate how efficiently winds transport heat from the day side toward the night side. An offset in peak brightness can indicate that atmospheric circulation has shifted the hottest region away from the point directly beneath the star. Some worlds show enormous temperature contrasts because their atmospheres cannot redistribute energy effectively. Others spread heat much farther around the globe. Phase curves therefore allow astronomers to study weather patterns without ever resolving clouds or continents. A distant planet brightens and fades by a tiny amount as it circles its sun. Hidden inside that rhythm is information about how an entire alien atmosphere moves energy around a world. Hidden planets can be inferred from the unusual timing of neighboring worlds. A planet that crosses its star should return at predictable intervals if nothing else is disturbing it. In a system containing several worlds, gravity complicates that perfect clockwork. Neighboring planets tug on one another as they move through their orbits. Those interactions can cause a transit to arrive slightly early on one occasion and slightly late on another. Astronomers measure these deviations with remarkable precision. If the pattern cannot be explained by the known planets, an additional unseen companion may be responsible. This approach allows researchers to detect a world without observing that world's own transit. Its gravity effectively changes the schedule of something we can see. The size and pattern of the timing shifts can reveal clues about the hidden planet's mass and orbit. Systems where planets pass near one another repeatedly can produce especially strong effects. The technique turns planetary systems into interconnected clocks. One clock running irregularly tells us that another hand is influencing the mechanism. A few minutes of unexpected delay in a distant transit can therefore expose an entire planet that never once crosses its star from Earth's point of view. One planet can expose another by repeatedly disturbing its neighbor's orbit. Planetary systems are not collections of isolated worlds following paths independently. Every planet attracts every other planet through gravity. Usually those tugs are small, but over repeated orbits they can accumulate into measurable changes. A hidden companion might alter a known planet's orbital period or change the shape of its path. In some systems, the perturbation causes the orientation of an orbit to shift gradually. That can even affect whether a transiting planet continues crossing the star from our viewpoint. By modeling these interactions, astronomers can test what unseen mass would be required to produce the observed behavior. This is planetary detection through consequences rather than direct signals. The method resembles the gravitational reasoning that revealed unseen bodies in the solar system long before exoplanets were known. Modern observations make the measurements vastly more precise. A planet hundreds of light years away can function as a natural detector for its own neighbors. Its orbit records every gravitational encounter. When that path deviates from what a lone planet should do, astronomers can investigate what invisible companion might be quietly rewriting the journey. Transit timing variations have uncovered planets that never cross their own stars. A multi-planet system can produce one of exoplanet astronomy's most satisfying forms of detective work. Suppose one planet transits regularly while another travels on an orbit tilted just enough to miss the stellar disk. The second world creates no transit signal of its own, yet its gravity can alter the schedule of the first. With enough observations, the pattern of early and late transits can become too structured to dismiss as noise. Astronomers then build dynamical models containing possible unseen companions and calculate how each arrangement would affect the observed planet. When one solution reproduces the timing changes consistently, the invisible world begins to take shape mathematically. Researchers may estimate its orbital period and mass despite never witnessing it pass in front of the star. This demonstrates why an exoplanet catalogue cannot be understood as a collection of simple detections. Some worlds are discovered through relationships. They become knowable because another planet responds to them. In these systems, gravity carries information from a planet we cannot observe directly into the orbit of one we can. Resonant planets can tug one another with remarkably precise gravitational rhythms. Sometimes two planets occupy orbits whose periods form a simple numerical relationship. One might complete roughly 2 journeys around the star, while another completes one. This arrangement is called orbital resonance. Each time the planets return to similar positions, their gravitational interaction occurs in a repeating pattern. Over time, those repeated tugs can produce large and highly organized variations in orbital timing. Resonances can preserve planetary configurations for immense periods, but they can also reveal clues about how the system formed and migrated. Planets probably do not always begin exactly where we see them today. Interaction with the disk of gas surrounding a young star can move them inward or outward. During that migration, neighboring worlds can become locked into resonances. Astronomers therefore read resonant patterns as both gravitational signals and pieces of planetary history. They can use the interactions to constrain masses, even when conventional velocity measurements are difficult. Two planets separated by millions of kilometers effectively keep time with each other. Their repeated gravitational encounters preserve a rhythm that observers can detect from across interstellar distances. Missing planets are sometimes predicted because known orbits refuse to behave normally. When astronomers calculate how a planetary system should evolve, the observed arrangement does not always fit comfortably. An orbit might precess unexpectedly. A planet's timing may drift in a pattern that known companions cannot reproduce. A debris structure might have an edge that seems too sharply sculpted to be accidental. These discrepancies invite a powerful question. What unseen object would make the system behave exactly as observed? Researchers can introduce hypothetical planets into computer simulations and vary their masses and orbits. Most possibilities fail. Others reproduce the puzzling feature surprisingly well. That does not immediately prove the planet exists, because alternative explanations must be tested. Yet predictions narrow the search. Astronomers can identify regions where the object should travel and estimate what kind of signal it ought to create. This reverses the usual discovery process. Instead of finding a planet and then calculating its effects, scientists notice the effects and calculate the planet. Hidden worlds become solutions to gravitational mysteries. Occasionally, later observations reveal the predicted companion. Even when they do not, the search forces researchers to understand the planetary system more deeply. Planet hunters can calculate where an unseen world should be before finding it. A planet leaves gravitational clues that contain more than the simple message that something is present. The direction and strength of those effects can constrain where the hidden object must travel. Imagine a ring of debris with one side repeatedly disturbed. A planet in certain locations would produce the wrong pattern, while another orbit might reproduce it naturally. Similar reasoning can be applied to stellar motion or interactions among known planets. Researchers explore thousands or millions of possible configurations with computers. Each model is allowed to evolve according to gravity. The survivors are the arrangements that resemble reality. These calculations can produce predicted ranges for mass, distance, orbital tilt, and current position. Telescopes can then search the most promising region rather than scanning blindly. The method remains probabilistic because another physical explanation may exist, but it transforms mystery into a testable forecast. Astronomy becomes predictive in a striking way. A planet may be missing from every image and catalogue, yet equations can describe where it ought to be. Observation then receives a simple challenge. Look there and determine whether nature actually placed a world in the calculated location. Neptune itself was discovered after mathematics predicted an unseen planet's gravitational pull. During the 19th century, astronomers noticed that Uranus was not moving exactly as calculations predicted. Its observed position drifted from the path expected under the influence of the known planets. Rather than abandoning Newtonian gravity, mathematicians considered another possibility. Perhaps an undiscovered planet was pulling on Uranus from farther out. Urbain Le Verrier in France calculated where such a world should appear. John Couch Adams in Britain independently worked on the same problem. In 1846, observers at the Berlin Observatory searched near Leverrier's predicted position and found Neptune. The planet was identified within a tiny fraction of a full circle from the calculated location. It was a spectacular demonstration of gravitational inference. Human beings had effectively detected a world with mathematics before recognizing it in a telescope. The episode became a model for later searches for hidden planets. Unexplained motion can be evidence rather than error. If gravity is understood well enough, an invisible body can announce its presence through what it does to something else. Neptune showed that an orbit can become a message from an unseen world. Similar detective work now searches for hidden worlds around distant stars. The stars in an exoplanet system are so remote that astronomers cannot watch individual planets tracing obvious paths around them. Yet the principle that revealed Neptune still applies. Gravity leaves consequences. Modern instruments simply measure those consequences in new ways. A star may shift position by an almost unimaginably small angle. A transiting planet may arrive minutes later than expected. A belt of dust might have a strange boundary that remains stable only if something massive is shaping it. Each discrepancy can be compared with simulations containing hypothetical companions. The enormous increase in computing power allows researchers to test complex systems that 19th century astronomers could never have calculated manually. At the same time, caution is essential. Stars are active objects, and disks of debris have their own complicated physics. Not every anomaly requires a planet. The strongest cases emerge when several independent observations point toward the same explanation. Planet hunting has therefore become a form of remote gravitational archaeology. Scientists cannot visit these systems. Instead, they study disturbances and reconstruct the invisible architecture responsible for them, sometimes predicting planets long before any direct glimpse becomes possible. Dust rings around young stars can contain gaps carved by unseen planets. Young stars are often surrounded by broad disks containing gas and microscopic grains. When radio telescopes image these disks at high resolution, they can reveal extraordinary structures. Bright rings alternate with darker gaps. Some systems contain several such divisions arranged almost concentrically around the star. One compelling explanation is that forming planets are clearing material from their neighborhoods. As a planet orbits, its gravity interacts with the disk and can push material away from particular regions. The result may be a gap much larger than the planet itself. Yet planets are not the only possible explanation. Changes in dust chemistry and other disk processes can also create rings. Astronomers therefore study the shape of each feature and compare observations with simulations. A gap containing additional disturbances can strengthen the planetary interpretation. What makes these disks so exciting is their age. Researchers may be looking at planetary systems during construction rather than billions of years afterward. The planets themselves can remain hidden inside dust. Their gravitational fingerprints appear first, etched into the material from which neighboring worlds may still be forming. Spiral patterns inside planetary nurseries may betray newborn worlds buried within them. Some protoplanetary disks do not display neat circular rings. Instead, enormous spiral arms curl through the material surrounding the young star. These structures can arise when the forming planet gravitationally disturbs the gas and dust. As the planet moves, its pull launches waves through the disk. Those waves can develop into spirals stretching far beyond the world responsible for them. Astronomers can compare the observed shapes with computer simulations to estimate what kind of planet might create the disturbance. The process is complicated because disks can also generate spirals through their own gravitational instability or interactions with companion stars. Researchers therefore look for supporting evidence near the suspected planet's location. Detecting a compact source embedded within the spiral would be especially persuasive. These observations offer something close to planetary forensics at the moment of birth. The infant world may be too deeply buried to photograph clearly, but the surrounding disk reacts to its gravity on an enormous scale. A planet only a tiny fraction of the disk's size can leave a spiral signature visible across billions of kilometers of its birthplace. Growing planets can hide inside the dusty disks that created them. Before a planetary system becomes a collection of clearly separated worlds, it begins as material orbiting a young star. Dust grains collide and stick together. Larger bodies grow through repeated impacts and gravitational attraction. Eventually, planetary embryos become massive enough to gather material rapidly from their surroundings. During much of this process, the forming planets remain embedded within the same disk that supplied their ingredients. That disk creates a serious observational obstacle. Dust absorbs and scatters visible light, while gas produces complex emission of its own. A young planet can therefore exist inside a bright and messy environment that conceals its exact position. Astronomers attack the problem with infrared and radio observations that penetrate or trace the disk differently. They also search for local disturbances caused by accretion and gravity. In a few remarkable systems, candidate protoplanets have been detected within gaps or cavities in the disk. These objects provide rare glimpses of planetary construction while it is still happening. Instead of studying the finished architecture, astronomers can investigate worlds while they are actively gathering the material that will define them. Newly forming worlds may glow where gas crashes onto their surfaces. A young giant planet can continue growing after its central body has already taken shape. Gas from the surrounding disk falls toward the planet under gravity. Before reaching the world, some of that material may pass through a smaller disk, encircling the planet itself. Eventually, gas plunges inward and releases energy as it decelerates. The resulting shock can become hot enough to produce distinctive radiation. Astronomers search for particular emission lines associated with this accretion process. Detecting them near a candidate planet can provide evidence that the world is still actively feeding. This is profoundly different from observing a mature planet that has settled into a stable existence. The object is being caught during construction. Its mass may be increasing while researchers watch. The surrounding environment can change over comparatively short astronomical timescales as material moves through the system. Accretion glow therefore serves as a beacon from an otherwise hidden newborn world. The planet may remain buried within dust and impossible to see as a recognizable globe, yet the violence of material falling onto it can reveal exactly where planetary growth is still underway. Planet formation begins inside disks so dusty that visible light cannot escape. Stars are born inside cold molecular clouds where gravity pulls dense concentrations of gas and dust together. As a young star forms, leftover material flattens into a rotating disk around it. This is the raw environment from which planets emerge. During the earliest stages, the system can be so heavily obscured that ordinary visible light telescopes cannot see into it at all. The dust grains absorb short wavelength radiation and re-radiate the energy at longer wavelengths. Infrared and radio observatories therefore become essential for investigating these hidden nurseries. They can reveal the distribution of material before the disk clears enough to become optically visible. This means some of the most important moments in a planet's history occur behind a curtain. Grain growth begins there. Larger bodies assemble there. The foundations of future orbital architecture may already be established before an external observer could see anything resembling a planetary system. Astronomy has learned to look beyond visible light precisely because nature often hides creation inside dust. The darkness around a newborn star can contain the beginnings of worlds long before those worlds emerge into view. Radio telescopes can peer through dust and expose structures shaped by infant planets. Radio astronomy has transformed the study of planetary birth because long wavelengths can reach us from regions that visible light struggles to penetrate. Networks of radio dishes can also be combined through interferometry, effectively creating a telescope with a resolving power determined by the distance between antennas. Facilities such as the Atacama Large Millimeter and Submillimeter Array can therefore map extraordinarily fine structures in disks around young stars. The resulting images have revealed rings and asymmetries that earlier observations blended together. Millimeter-sized dust grains emit strongly at these wavelengths, allowing astronomers to trace where solid material is concentrating. Those concentrations matter because they may mark regions where planet formation is especially active. Gas molecules produce their own spectral lines and reveal how material moves through the disk. Researchers can search for disturbances in velocity that might indicate a hidden planet altering the local flow. Radio telescopes are not simply seeing through dust as though it were transparent. They are observing an entirely different form of radiation produced by the material itself. Planetary nurseries that look dark in visible light become detailed laboratories when viewed at wavelengths human eyes cannot detect. Some young planets may still be surrounded by their own miniature disks. A giant planet forming inside a large stellar disk can gather enough material for a second disk to develop around the planet itself. This structure is called a circumplanetary disk. It is essentially a tiny planetary nursery, nested inside the larger nursery surrounding the star. Gas and dust entering the planet's gravitational domain do not necessarily fall straight downward. Their angular momentum causes material to orbit first, creating a flattened structure. Astronomers have found compelling observational evidence for such disks around young planetary candidates. These environments are important because they help regulate how rapidly the planet gains mass. They also provide a natural setting for building satellites. The scale is astonishing. A telescope looking at a distant young star may be studying a disk containing a forming planet that possesses another disk of its own. Each level is governed by the same basic principles of gravity and rotation, but on dramatically different scales. Circumplanetary disks allow astronomers to investigate not only how planets finish growing, but also how entire miniature systems can begin developing around them before the parent planetary system itself is complete. Those miniature disks could eventually produce moons around the growing planet. The major moons of Jupiter and Saturn may preserve evidence of processes that operated while their planets were still young. In one leading picture, material orbiting a growing giant planet forms a circumplanetary disk. Dust and ice within that disk collide and accumulate much as material does inside a larger protoplanetary disk around a star. Small moonlets emerge fast. Continued collisions and gravitational interactions can build larger satellites. The process helps explain why several large moons follow orderly paths close to their planet's equatorial planes. Their formation was tied to the rotating material surrounding the young giant. Circumplanetary disks can evolve quickly as gas drains onto the planet or disperses into space, so moon formation must occur during a limited window. Some early satellites may even spiral inward and be lost before the surviving system takes shape. Observing these disks around distant young planets gives astronomers a chance to test whether similar processes operate elsewhere. A faint structure surrounding a hidden newborn planet may therefore represent more than leftover material. Inside it, another generation of worlds could already be assembling on a much smaller scale. Dust rings around young stars can contain gaps carved by unseen planets. Planetary systems can eject worlds through violent gravitational encounters during their youth. Young planetary systems are not always orderly places. Several growing planets can begin on paths that bring them close enough for their gravity to reshape one another's orbits. Most encounters simply alter those paths, But occasionally, a planet receives such a powerful gravitational kick that it is thrown beyond the star's control. From that moment, the world becomes an interstellar traveler. Computer simulations suggest this kind of instability can happen while planetary systems are settling into their final arrangements. Giant planets are especially influential because their gravity can scatter smaller neighbors across enormous distances. The process may also leave survivors on stretched or tilted orbits, creating systems that look strangely disordered billions of years later. Our own solar system probably experienced substantial rearrangement during its youth, although its major planets remained bound to the Sun. Elsewhere, the outcome may have been much harsher. A world that spent millions of years growing beside a star can lose that star during a single close encounter. Planet formation does not merely create worlds. Sometimes it creates them and then throws them away. Smaller planets are easier to fling completely free from their parent stars. During a close gravitational encounter, planetary mass can make an enormous difference to the outcome. A lightweight world is easier for a massive neighbor to accelerate into a radically different orbit. If that kick raises its speed beyond the local escape velocity, the smaller planet no longer follows a closed path around the star. It leaves the system entirely. Giant planets tend to be much harder to eject because changing the motion of so much mass requires a stronger interaction. They are therefore more likely to act as the gravitational bullies than the victims. Simulations of unstable systems frequently show smaller worlds being scattered outward, while larger planets remain behind. This raises an intriguing possibility about the hidden rogue population. Many wandering planets could be rocky or icy bodies rather than enormous gas giants. Those smaller objects are also the most difficult for us to detect once they enter interstellar space, which means the population could be strongly underestimated. The worlds most easily expelled by gravity may become the worlds most effectively concealed from astronomy after their departure. An expelled planet could carry moons with it into interstellar darkness. Being thrown from a planetary system does not automatically strip a planet of everything orbiting it. A moon travels primarily under the gravity of its planet, so a sufficiently close satellite could remain attached while the pair escapes their star. Numerical studies show that some moons can survive planetary ejection, although distant satellites are easier to lose during the violent encounter. The result would be one of the strangest systems imaginable. A planet and moon could continue circling their shared center of mass while both travel independently through the galaxy. Their sky would contain stars, but no nearby sun would dominate it. The moon could still create tides inside the planet if oceans or flexible layers survived beneath the surface. In return, the planet would remain an enormous object in the moon's sky despite the absence of daylight. Detecting such a partnership would be extraordinarily difficult because neither object would normally shine brightly. Yet it is physically possible. A planetary system does not always require a star. Sometimes the smallest surviving fragment of one could be a world and its moon traveling together after everything larger has been left behind. Some rogue worlds may form alone without ever belonging to any star. Not every planetary mass object necessarily began inside a planetary system. Clouds of cold gas can collapse under gravity and form isolated bodies without producing a normal star. If the collapsing fragment contains too little mass to sustain hydrogen fusion, the result can resemble a planet even though it formed more like a miniature star. This creates an awkward boundary in astronomy. Two objects with similar masses and temperatures could have completely different histories. One may have formed in a disk and later been ejected. The other may have condensed directly from a cloud and never orbited anything. Researchers sometimes call the lowest mass isolated examples free-floating planetary mass objects rather than planets, because formation history matters to classification. Observations of young star-forming regions have uncovered surprisingly lightweight bodies traveling independently among the stars. Studying them helps astronomers test how small a collapsing cloud fragment can become. It also complicates estimates of the rogue population. Interstellar space may contain both planetary refugees and objects born there from the beginning. They can look remarkably similar today, even though their origins could not have been more different. A starless planet can still retain internal heat for billions of years. Sunlight is only one source of planetary warmth. Worlds also contain energy left behind during their formation and differentiation. As material assembled under gravity, impacts and compression heated the growing planet. Heavy elements sank inward while lighter material rose, releasing additional gravitational energy. Much of that ancient heat can take an extraordinary length of time to escape through thousands of kilometers of rock or dense fluid. Giant planets possess another source because their interiors slowly contract under gravity, converting potential energy into heat. Jupiter still radiates more energy than it receives from the Sun. An isolated giant would therefore not instantly freeze when separated from its star. It would gradually cool as its internal reservoir leaked into space. Even rocky worlds can preserve substantial heat deep underground long after their surfaces become frigid. The outside of a rogue planet might be extraordinarily cold while the interior remains geologically active. Darkness would conceal a world that was not truly frozen throughout. Remove the star and you remove daylight, but you do not immediately remove the energy stored inside a planet's own history. Thick atmospheres could keep some rogue planets warmer than their surroundings suggest. A wandering planet receiving almost no starlight might seem destined for extreme cold, yet atmosphere can change the calculation dramatically. Certain gases absorb infrared radiation leaving the surface and return part of that energy downward. On Earth, this greenhouse effect depends heavily on energy originally supplied by the Sun. A rogue world would instead rely on heat escaping from its interior. If the atmosphere were thick enough and contained effective infrared absorbers, that modest internal energy could become trapped far more efficiently than it would beneath a thin atmosphere. The surface might remain dramatically warmer than the planet's distance from any star suggests. Hydrogen is particularly interesting because dense hydrogen atmospheres can impede heat loss through collision-induced absorption. Models have shown that under suitable conditions, an Earth-mass rogue planet could potentially maintain surface temperatures compatible with liquid water for long periods. Whether nature actually produces many such worlds is unknown. Their atmospheres must survive ejection and avoid escaping over time. Still, a starless planet does not have to be an exposed ball of ice. An atmosphere can fundamentally rewrite what darkness means for its climate. Subsurface oceans might remain liquid on worlds receiving no warmth from starlight. Ice can act as insulation as well as evidence of cold. If a rogue planet contains enough water, its surface may freeze while heat from deeper inside continues rising through the crust. Once a thick layer of ice develops, that shell can slow the loss of energy from the liquid below. Under suitable conditions, an ocean could survive beneath kilometers of frozen surface, even though the world receives essentially no stellar warmth. Our own solar system already demonstrates the basic principle. Several icy moons are thought to contain internal oceans despite living far from the Sun's strongest heating. A rogue planet could possess a much larger reservoir and stronger internal energy depending on its mass and composition. Life beneath such an ocean would face an environment unlike Earth's sunlit surface, but sunlight is not required for every conceivable metabolism. Chemical reactions between water and rock could provide usable energy. Nobody knows whether inhabited rogue oceans actually exist. What makes the possibility extraordinary is that a planet could look dead and frozen from space, while an entire liquid environment remains sealed underneath. Radioactive elements can provide hidden planets with heat long after formation. Rocky planets contain unstable isotopes that slowly transform into other elements. Each decay releases a small amount of energy, but across an entire planet, the total can become geologically important. Uranium, thorium, and potassium contribute to Earth's internal heat today. The same physics should operate on rocky worlds elsewhere if they formed with comparable radioactive materials. Unlike leftover formation heat, radioactive heating can continue as long-lived isotopes decay over billions of years. This can help sustain mantle movement and possibly volcanism long after a planet's surface has cooled. For an isolated world, those reactions become especially important because no nearby sun replenishes surface energy. The amount of heat would depend strongly on the planet's chemical history. Worlds born from material rich in radioactive elements could remain more active than otherwise similar planets with smaller inventories. Deep geological activity might also circulate water through warm rock and create chemical gradients beneath frozen surfaces. A rogue planet can therefore carry a small nuclear furnace inside its own minerals. No reactor was built there. Ordinary atoms inherited during planetary formation quietly release energy across spans of time longer than civilizations can easily imagine. A wandering world could cross the galaxy without experiencing a single sunrise. Once separated from its star, a rogue planet no longer possesses a normal day defined by sunrise and sunset. It may still rotate on its axis, but that rotation only changes which distant stars appear overhead. No nearby sun rises to flood the landscape with daylight. Depending on its trajectory, the planet could travel for billions of years through the Milky Way, while never entering another stellar system closely enough to acquire a new sun. Space between stars is immense, and direct encounters between planets and stars are exceptionally rare. The sky from such a surface would therefore remain permanently dark in the ordinary sense. The Milky Way itself could stretch overhead if an atmosphere allowed it to be seen. Occasional nearby stars might become brighter as the planet moved through different regions of the galaxy, but none would behave like the Sun does for Earth. This is not a temporary polar night caused by seasons. It is a planetary existence with no dawn built into its normal environment. Entire geological ages could pass beneath a sky that never once becomes daytime. Rogue planets are nearly impossible to count because most never announce themselves. Astronomers can estimate the number of ordinary stars by surveying large regions and correcting for objects too faint to detect. Rogue planets present a much harder census problem because they lack the luminous markers that usually tell researchers where planetary systems are located. The coldest examples may emit so little radiation that even nearby ones remain difficult to identify directly. Gravitational lensing can expose them, but only when chance alignment places a useful background star behind them. A survey therefore samples a tiny fraction of the wandering population at any given time. Scientists must take the events they do observe and infer how many unseen objects are required to produce them. That calculation depends on the masses and velocities of the lenses, as well as the structure of the galaxy. Small changes in assumptions can alter the estimated population substantially. This is why published estimates have varied over time. The uncertainty is itself revealing. Astronomy is trying to count objects designed by circumstance to avoid being counted. The Milky Way could contain an enormous population of wandering worlds, while giving us only brief statistical glimpses of their true abundance. Short micro-lensing events can reveal objects roughly as massive as Earth. The duration of a gravitational microlensing event contains clues about the mass of the object causing it. Massive lenses generally influence light across larger regions and produce events that unfold more slowly. A planetary mass object creates a much smaller gravitational lens, so the alignment can sweep past quickly. For something around Earth's mass, the most noticeable brightening may persist for only a matter of hours. That makes these events both exciting and difficult. Researchers must distinguish genuine lensing from stellar flares or other brief changes in brightness. Dense monitoring is essential because missing even part of the event can leave its shape poorly constrained. The absence of an obvious host star signal nearby can make the object a candidate free-floating planet. Additional observations are often needed before researchers can decide whether a distant host might simply have escaped detection. Even with those uncertainties, very short events open an observational doorway that conventional planet searches rarely provide. They can uncover small dark objects traveling through the galaxy without asking those objects to orbit visible stars. For a few hours, gravity makes an Earth mass traveler measurable. The smallest gravitational lenses may brighten background stars for only a few hours. Planet hunters working with microlensing live with a peculiar problem. The most intriguing low-mass objects can produce some of the shortest opportunities to study them. As a small lens crosses the line of sight, the useful alignment can develop and disappear during a single night. There may be no warning days beforehand that a planetary event is approaching. Survey telescopes therefore scan their fields repeatedly and use automated systems to recognize unusual changes quickly. High-cadence observations capture the rise and fall of brightness in enough detail to distinguish lensing from ordinary stellar variability. Weather can become scientifically important because clouds over one observatory might erase a crucial part of the light curve. Networks of telescopes at different longitudes help provide continuous coverage as Earth rotates. The brief duration is not merely an inconvenience. It is part of the evidence that the lens may possess very little mass. In this branch of astronomy, an event disappearing quickly can make it more interesting. A few hours of altered starlight may be the only detectable trace that a tiny, unseen world ever crossed our line of sight. Planet hunters must monitor enormous star fields to catch these fleeting events. Microlensing cannot usually be scheduled around a known planet because astronomers do not know where the lensing object is beforehand. Instead, surveys watch huge populations of distant stars and wait for chance alignments to occur. Crowded regions of the Milky Way are ideal because every monitored star creates another possible background light source. Modern cameras can track millions of stars repeatedly, producing vast datasets in which automated software searches for characteristic brightening patterns. Most stars do nothing interesting during a given observing period, a tiny fraction change for reasons connected with lensing. Within that fraction, only some events contain planetary signatures. This makes microlensing astronomy a search for rare geometry, hidden inside an overwhelming amount of ordinary starlight. The method becomes more powerful as the number of monitored stars rises and the interval between observations shrinks. Computing is therefore as essential as optics. No human team could inspect every measurement manually. Algorithms identify candidates so researchers can concentrate on the exceptional cases. Catching a hidden planet can begin by watching an almost absurd number of unrelated stars and waiting for one of them to behave differently. The crowded center of our galaxy is especially valuable for microlensing searches. Look toward the central bulge of the Milky Way, and countless stars overlap along our line of sight. For many kinds of observation, this crowding is a nuisance. For gravitational microlensing, it creates opportunity. Every distant star in the bulge can serve as a background source. Between Earth and those stars lie many potential lenses moving independently through the galaxy. That combination dramatically increases the probability of useful alignments. Planet searchers, therefore, devote intensive observing campaigns to fields near the galactic center. The region is challenging because dust absorbs visible light, and so many stellar images blend together. Careful image analysis is needed to determine which source actually brightened. Infrared observations can help penetrate dusty areas and expand the accessible population. The reward is statistical power. One relatively small patch of sky can provide more lensing opportunities than enormous emptier regions elsewhere. Our position inside the galactic disk means we are looking through a tremendous depth of stars when we face inward. The Milky Way's most crowded direction effectively becomes a vast natural laboratory for detecting masses that cannot be seen themselves. NASA Roman telescope is designed to uncover planets ordinary surveys routinely miss. The Nancy Grace Roman Space Telescope will approach planet hunting from a region of space that has remained comparatively poorly sampled. Its wide-field camera is designed to monitor dense star fields with the stability available above Earth's atmosphere. One major program will use gravitational microlensing to search for planets across a broad range of masses and orbital distances. This complements missions that primarily excel at finding close-in transiting worlds. Roman's combination of wide coverage and sharp imaging should allow it to separate crowded stellar sources more effectively than many ground-based surveys. The mission is particularly exciting for hidden planets because it can detect worlds that do not produce convenient repeating transits. It should also provide a more systematic census of free-floating planetary mass objects. Rather than discovering only occasional examples, astronomers expect to build population statistics that can test how frequently planetary systems eject worlds. The important change is not simply finding more planets. It is finding a different population. Every major detection technique has favored certain architectures. Roman is intended to illuminate part of the planetary landscape that current catalogues represent far less completely. Roman should reveal colder worlds occupying orbits more like our outer planets. Much of the exoplanet revolution has been dominated by planets that orbit surprisingly close to their stars. Those worlds create frequent signals, which makes them efficient targets for surveys. Roman's microlensing program will be sensitive to a different region. It can detect planets located around or beyond the distance where water would have frozen into ice within the original planet-forming disk. This region is often called the snow line. Giant planets are thought to form efficiently there because solid material becomes more abundant once volatile compounds freeze. Jupiter and Saturn occupy the outer part of our own planetary system, so finding comparable architectures elsewhere is essential for understanding whether our arrangement is unusual. Microlensing does not require a planet to complete repeated orbits during the mission. One fortunate alignment can expose a world whose year would otherwise be inconveniently long. Roman should therefore help fill the enormous observational gap between close exoplanets and the cold giants familiar from our own solar system. The result may finally show how common distant planetary systems resembling ours are throughout the galaxy. Microlensing can find planets far beyond the distances favored by transit surveys. Transit surveys are exceptionally successful when planetary years are short. A world that circles its star every few days can cross the stellar disk many times during a mission. Move that same world much farther outward, and the situation changes. It may transit only once or never during the available observations. Microlensing does not care how frequently the planet orbits. The crucial event is the alignment between the lensing system and a distant background star. That gives the method access to planets whose enormous orbital periods would frustrate repeated transit searches. It is particularly useful around the region where giant planets are expected to have formed and beyond it. The technique, therefore, expands the exoplanet map outward. It can reveal planetary territory that would remain nearly blank if astronomers relied on transits alone. This matters when estimating what typical planetary systems actually look like. A catalogue dominated by close worlds can create a distorted impression of nature. Microlensing supplies another perspective by finding planets that live where years are long and stellar warmth is much weaker. Recent surveys suggest super-Earths may be common on surprisingly wide orbits. Super-Earths are worlds more massive than our planet, but substantially lighter than the solar system's giant planets. Many early discoveries placed them close to their stars because those were the easiest versions to detect. Microlensing observations have increasingly shown that similar mass worlds also exist much farther out. This matters because planetary formation theories must explain not only how these planets grow, but how they become distributed across such different regions. A distant super-Earth would experience far lower temperatures than the compact examples found through transits. Depending on its composition, it might resemble a massive rocky planet or contain thick layers of volatile material. Wide-orbit super-Earths are particularly interesting because our own solar system has nothing in that mass range. Earth is followed by much larger Uranus and Neptune, leaving a conspicuous gap. Other systems appear not to share that arrangement. If distant super-Earths prove abundant, our planetary neighborhood may look unusual for lacking one. The hidden outskirts of other systems could therefore contain a class of planet that is common throughout the galaxy but completely absent from the place where humanity first learned what planets are. Uranus-mass planets have been discovered hiding beyond their system's frozen snowlines. The snowline marks a major transition inside a young planetary disk. Far enough from the star, temperatures become low enough for water and other volatile substances to freeze onto grains. That creates more solid material from which growing planets can build. Worlds with masses comparable to Uranus are therefore especially interesting when found beyond this boundary. They occupy a region where theories expect icy planetary cores to develop before gathering surrounding gas. Microlensing has revealed planets in this general regime, even when the systems lie thousands of light-years away. Such discoveries provide clues about an important stage between rocky super-Earths and gas giants like Jupiter. Uranus and Neptune contain substantial amounts of heavier material beneath hydrogen-rich outer layers, yet we have only 2 nearby examples to study. Finding counterparts elsewhere allows astronomers to ask whether our ice giants represent a common outcome or an unusual one. Each distant detection adds another point to a population we are only beginning to measure. Cold intermediate-mass planets may be plentiful, even though conventional exoplanet catalogues have historically struggled to expose them. Ice giants may be far more common than our current catalogue suggests. Uranus and Neptune are easy to overlook when people imagine the major kinds of planets. Rocky Earths and enormous gas giants occupy the familiar extremes. Ice giants sit between them with a distinctive internal structure. Their bulk is thought to contain large proportions of compounds such as water, methane, and ammonia, alongside rock and hydrogen-rich gas. Detecting equivalent worlds around other stars is difficult because their masses are modest compared with Jupiter, and their likely orbits can be long. That combination produces weak or slowly changing signals. Yet planet formation models frequently generate worlds in this intermediate range. Microlensing discoveries also indicate that cold planets below Jupiter's mass are not rare. If future surveys uncover large numbers of them, one of the major hidden populations in the galaxy could turn out to resemble the type of planets sitting in the outer solar system all along. This would change how astronomers think about planetary systems. Uranus and Neptune might not be odd leftovers between better-known categories. They could instead represent a widespread class of world that our current discovery methods happen to undercount. Worlds like Uranus and Neptune are surprisingly difficult to detect around other stars. An ice giant occupies an awkward observational middle ground. It is not massive enough to produce the enormous stellar motion caused by a Jupiter-sized companion. If it lives far from its star, Its orbit may take many years and provide few opportunities for repeated measurements. Its temperature can also be low enough to make direct infrared detection difficult after the system has aged. Transit probability falls as orbital distance increases, which removes another powerful discovery route. These effects combine into an observational blind spot. Astronomers have found many planets with radii similar to Neptune when they orbit close to their stars, but true analogues of the cold outer planets are much harder to establish. This limits our ability to compare complete planetary architectures. A star that appears to possess only inner worlds may also host distant ice giants that remain below detection thresholds. Those planets could strongly influence the evolution of comets and smaller bodies, while barely announcing themselves to observers on Earth. One of the most familiar planetary types in our own system may therefore be among the least completely surveyed types in everybody else's. A distant solar system twin could hide every planet from transit searches. Imagine placing our solar system around another sun-like star and viewing it from a direction well above the plane of the planets. Mercury would never cross the star from that perspective. Neither would Venus, Earth, Jupiter, or any of the others. A transit survey could monitor the system with exquisite precision for years and receive no planetary eclipse at all. The system would not be empty. Its orientation would simply hide the entire family. This thought experiment exposes a crucial limitation of transit astronomy. Planets in the same system often share broadly similar orbital planes because they formed from one flattened disk. If that common plane misses the line between the star and Earth, several worlds can disappear from transit searches together. Other techniques might eventually reveal them, but some signals would be extremely small or slow. An astronomer living around a distant star could therefore study our Sun and initially conclude that no transiting planets were present. Earth itself would contribute nothing to that particular search. A complete planetary system can remain invisible, not because its worlds are unusual, but because we happen to be looking from above. Planet surveys are biased toward worlds that are easiest for our instruments to notice. Every exoplanet catalogue is shaped by selection effects. Large planets block more starlight during transits than small ones. Massive planets exert stronger gravitational pulls. Hot young planets glow more brightly in infrared images. Short orbital periods repeat rapidly and can be confirmed sooner. None of these qualities necessarily makes such worlds intrinsically common. They make them detectable. Astronomers therefore cannot simply count the planets in a catalogue and declare that the most numerous entry represents the galaxy's most numerous planet. They calculate how sensitive each survey was to different sizes and orbital arrangements. If a telescope would have detected almost every hot Jupiter in its sample, but only a tiny fraction of distant Earth-sized worlds, those raw discovery numbers mean very different things. Correcting these biases is one of the central challenges of exoplanet statistics. Our instruments act like filters placed between reality and the catalogue. Understanding the filter is essential before interpreting what comes through it. Hidden planets are not always physically concealed. Sometimes they are hidden by the design limitations of the very experiments intended to find them. Our picture of planetary diversity changes whenever a new detection method opens. The first major waves of exoplanet discoveries repeatedly surprised astronomers because each technique exposed worlds that earlier methods had barely sampled. Precision velocity measurements revealed giant planets racing around their stars in only a few days. Transit surveys later uncovered enormous populations of smaller, close-in worlds. Direct imaging opened access to young giants on extremely broad orbits. Microlensing began revealing colder planets at distances where conventional surveys were less sensitive. None of these methods provides the whole picture alone. Together, they have shown that planetary architecture is far more varied than the solar system once suggested. This pattern gives astronomers reason to expect further surprises. A future technique that becomes sensitive to another poorly explored region may uncover a population that currently looks rare only because we struggle to detect it. Planetary diversity is therefore partly a history of technological thresholds. Nature did not suddenly create these strange worlds when instruments improved. They were always there. What changed was the portion of reality that our measurements could reach. Each new method removes another layer of invisibility from the galaxy. Hot Jupiters seemed common partly because enormous close planets are easy targets. When planets were first discovered around sun-like stars, some of the earliest examples looked almost absurd. Jupiter-mass worlds were orbiting astonishingly close to their suns and completing years in only a few Earth days. Astronomers had not expected giant planets to be so near their stars because our own Jupiter lives far outside the inner solar system. For a time, the discoveries made these extreme systems seem almost characteristic of exoplanets. The explanation was largely observational. A huge planet in a tight orbit produces a strong gravitational signal that repeats quickly. If its orbit is aligned for transits, its large size also blocks a conspicuous fraction of starlight. These planets were therefore unusually easy for early surveys to confirm. As detection sensitivity improved, much larger populations of smaller worlds emerged, and hot Jupiters became recognized as comparatively uncommon. Their early prominence offers a cautionary lesson. The first things we discover are often the things nature makes easiest to notice. A spectacular population can dominate astronomy's attention long before researchers learn whether it dominates the galaxy itself. Cooler planetary systems may dominate the galaxy while remaining seriously undercounted. The regions far from stars are intrinsically difficult places to survey. Planets there move slowly and receive little radiation. Yet planet formation occurs across broad disks that extend well beyond the compact zones emphasized by many discovery techniques. This creates the possibility that much of the galaxy's planetary population occupies colder territory than our catalogues suggest. A system might contain several distant worlds while offering observers only one easily detected inner planet. Another star might possess nothing close enough to produce frequent signals at all. Statistical studies attempt to reconstruct these missing populations, but the uncertainties grow in regions where sensitivity drops sharply. Cold worlds matter because they preserve different chemistry and formation histories from intensely irradiated planets. Volatile materials can remain abundant, and atmospheric evolution proceeds under very different conditions. Understanding them is essential if astronomers want a complete theory of how planetary systems form. The familiar exoplanet map may therefore be brightest exactly where our instruments are strongest, not where planets themselves are most abundant. Beyond those well-sampled regions could lie a much larger population existing in comparative observational darkness. Small planets on long orbits combine two qualities that make detection exceptionally difficult. Reduce a planet's size and several signals immediately weaken. Move that same planet farther from its star and the remaining opportunities become less frequent. Together, these changes create one of planet hunting's toughest combinations. A small world blocks very little light during a transit. A long orbital period means astronomers may need years before seeing that transit repeat. Its low mass creates only a slight gravitational effect on the star, while its cold temperature makes direct thermal detection challenging. Even if such planets are common, they can remain rare in catalogues because almost every major technique struggles with them. Earth itself illustrates the problem. Around a distant sun-like star, it would cross the stellar disk only once per year if the geometry were perfect. A world orbiting farther out would offer even fewer chances. This observational gap matters whenever astronomers discuss the frequency of potentially familiar planetary environments. The planets people often want most to find are among those nature has made hardest to detect. Rarity in our databases can therefore reflect difficulty rather than genuine scarcity. An Earth twin around a Sun-like star produces only a tiny stellar wobble. Earth's gravity moves the Sun just as every planet moves its host star, but the effect is extremely small. Viewed from far away along a favorable direction, the Sun's velocity change caused by Earth would be measured in mere centimeters per second. That signal is smaller than many disturbances created naturally on a star's surface. Detecting it requires spectrographs with extraordinary stability and an understanding of stellar behavior, precise enough to separate planetary motion from the star's own noise. Temperature changes and magnetic activity can alter the shapes of spectral lines. Convection across the stellar surface can shift them as well. Researchers seeking true Earth analogues are therefore pushing radial velocity measurements into a regime where the star itself becomes one of the largest obstacles. A Jupiter-like planet announces itself much more strongly because of its greater mass. Earth barely nudges the Sun. Finding its distant equivalent means detecting that minuscule pull across light years. The world could possess oceans and continents, while its gravitational announcement to us amounts to a stellar motion slower than an ordinary person walks. Finding another true Earth requires distinguishing planetary signals from activity on its star. Stars are not perfectly stable lamps. Their surfaces boil with convection and magnetic fields. Dark spots rotate in and out of view. Bright active regions appear elsewhere. These changes can alter the spectrum in ways that resemble the motion produced by an orbiting planet. For large planetary signals, stellar activity may be manageable. For an Earth-like world around a Sun-like star, the unwanted stellar effects can be larger than the signal researchers are trying to detect. Astronomers therefore monitor activity indicators alongside velocity measurements. They study how different spectral lines respond and look for patterns connected to the star's rotation. Observations across long periods help separate magnetic cycles from true orbital repetition. The challenge becomes especially demanding because an Earth analog would require roughly a year to circle its star. So patience and instrument stability are essential. Discovering such a world is not simply a matter of building a more sensitive detector. Scientists must understand the star almost as carefully as the planet. Before a tiny gravitational rhythm can be trusted, the much louder behavior of the distant Sun has to be decoded. Star spots can imitate the gravitational fingerprints astronomers use to discover planets. A dark star spot changes the balance of light coming from a rotating stellar surface. When the spot appears on the side rotating toward Earth, it removes some light that would otherwise be slightly blue-shifted. Later, as the spot moves across the star, it affects regions with different rotational velocities. The combined spectrum can shift in a way that resembles the star moving backward and forward under a planet's gravitational pull. If the spot persists for several rotations, the full signal can even repeat. This has caused genuine confusion in planet searches. Astronomers cannot assume that every periodic velocity variation comes from an orbiting world. They examine the shapes of spectral lines and compare the suspected period with the star's rotation. Changes in chromospheric activity provide further clues. Star spots also evolve, so their signals often change in ways stable planetary orbits do not. Distinguishing the two becomes especially important when searching for lightweight planets. A feature on the surface of a star can create a convincing ghost of a planet, demonstrating that some hidden worlds disappear when astronomers understand their suns better. Stellar magnetic cycles can create convincing signals that later prove planetary imposters. A star's magnetic behavior can unfold over years, which makes it especially dangerous for planet hunters searching for long orbital periods. Our Sun goes through an activity cycle lasting roughly 11 years. Other stars have cycles of their own. As magnetic regions appear and disappear, they change how hot gas rises through the stellar surface. That alters the shapes and positions of spectral lines. To an astronomer measuring radial velocity, the result can resemble the slow pull of an unseen planet. The illusion may persist through many observations because the magnetic cycle itself is regular. Researchers therefore compare suspected planetary signals with independent signs of stellar activity. Certain spectral features become stronger when magnetism increases. Measurements of brightness can reveal related changes. If the apparent planet rises and falls in step with those indicators, suspicion grows that the star is fooling the observer. This is particularly important for proposed worlds with years lasting several Earth years. A patient magnetic star can imitate a patient planet. Sometimes the object disappearing from a planetary catalogue is not a failure of astronomy. It is evidence that astronomers have learned to read the star more accurately. Some celebrated planet discoveries have disappeared after better observations exposed false signals. Exoplanet astronomy contains genuine reversals. A signal can look persuasive when first discovered and then weaken as additional measurements arrive. One famous example involved planets proposed around Captain's star. Early radial velocity data suggested several worlds, including one that attracted attention because its orbit appeared potentially temperate. Later analysis indicated that at least part of the signal was connected to stellar activity rather than an orbiting planet. Similar disputes have occurred around other stars. This is why confirmation matters more than excitement. A periodic pattern can arise from rotation, magnetic behavior, instrumentation, or statistical coincidence. Additional years of observations may shift the apparent period or reveal that the signal changes when a real orbit should remain predictable. A planet can therefore exist in scientific literature for a time before becoming doubtful or disappearing entirely. That process is not astronomy breaking down. It is astronomy correcting itself. Hidden planet research operates near the limits of measurement, where nature can produce extraordinarily convincing imitations. Sometimes the most important discovery is learning that a fascinating world probably was not there after all. Confirming a hidden planet often requires several completely independent lines of evidence. The strongest exoplanet discoveries become convincing when different measurements tell the same story. A transit can reveal how large a planet appears relative to its star. Radial velocity observations can then test whether an object with mass is actually orbiting on the same schedule. Precise imaging may rule out a second star in the background that could imitate the transit. Researchers can also examine whether the signal remains consistent over many orbital cycles. Each test attacks a different possible explanation. This matters because false positives can be surprisingly sophisticated. An eclipsing binary star blended with another star can mimic the dimming expected from a planet. Stellar activity can create an apparent gravitational rhythm. Instrumental effects can manufacture patterns that look periodic. No single clue needs to carry the entire case when several independent techniques are available. The most secure discoveries survive attempts to explain them without a planet. This gives hidden worlds an unusual route into certainty. Astronomers may never see the globe itself, yet a collection of unrelated measurements can eventually leave almost no plausible explanation except that a planet really is there. Binary stars can mimic planetary motions and complicate searches for unseen companions. Not every invisible object pulling on a star is a planet. A faint companion star can produce gravitational motion that initially resembles the influence of a massive world. If the companion is small or difficult to separate from the brighter primary star, its light may remain buried in the combined observation. Binary systems can also generate complicated spectral patterns because two sets of stellar lines shift as the stars orbit one another. Under some circumstances, those blended lines can create misleading velocity signals. Astronomers therefore investigate suspected planetary systems for hidden stellar companions. High-resolution imaging can search for nearby points of light. Spectroscopy can reveal a second set of lines. Measurements of the star's movement across the sky can constrain the mass of whatever is pulling it. This distinction is crucial because the boundary between giant planets, brown dwarfs, and low-mass stars can be difficult to establish from incomplete information. A signal announcing a seemingly remarkable planet may instead belong to a tiny star. Before celebrating a hidden world, researchers must first determine whether the darkness beside the target contains something far more massive. Planets around double stars can follow orbits unlike anything in our solar system. A planet living in a binary system can experience gravitational conditions with no close equivalent around the Sun. Some worlds orbit both stars at once from a comfortable distance. Others circle just one member of the pair, while the second star moves farther away. The stability of either arrangement depends strongly on distance and orbital geometry. Place the planet in the wrong region and repeated gravitational tugs can eventually throw it onto a chaotic path. Stable systems can still experience dramatic long-term changes in orbital shape or orientation. The second star can alter the planet's seasons by changing how much light reaches it over time. It can also affect the disk from which the planet originally formed. Astronomers once wondered whether binary stars might prevent planets from forming efficiently. Discoveries have shown that nature can build planetary systems even in these complicated environments. That matters because binary and multiple stars are common throughout the galaxy. A large fraction of hidden planets may therefore inhabit systems where the simple picture of one star controlling one family of worlds does not apply. Some circumbinary worlds remain hidden because two moving suns complicate every measurement. A planet that circles two stars does not necessarily transit with clockwork regularity. The stars themselves are orbiting each other, so they occupy different positions each time the planet returns. One transit may occur earlier than a simple planetary period predicts. Another may last longer because the star being crossed is moving in a different direction. Sometimes several expected crossings vanish entirely because the geometry no longer lines up. These irregularities once looked like obstacles. They later became powerful evidence for circumbinary planets because ordinary single-star systems cannot reproduce the same pattern. Finding them still requires specialized analysis. Automated searches designed for evenly spaced transits can overlook signals that wander substantially in time. Researchers instead model the motions of all three bodies together. The result can reveal orbital configurations that look chaotic at first glance, but follow precise gravitational rules. A planet around two suns can therefore hide inside data precisely because it refuses to behave like the worlds our software was originally trained to find. The unusual timing is not noise. It is the fingerprint of a more complicated planetary system. Pulsars can expose planets through astonishingly precise changes in their repeating radio pulses. A pulsar is a rapidly rotating neutron star that sends beams of radio waves across space. When one of those beams sweeps past Earth, telescopes record a pulse. Some pulsars rotate with such extraordinary regularity that their arrival times rival the stability of human-built clocks. An orbiting planet shifts the pulsar slightly around the shared center of mass. That changes the distance the radio signal must travel to Earth. The difference can amount to tiny fractions of a second, yet pulsar timing is precise enough to measure it. Repeated variations reveal the planet's orbital period and provide clues about its mass. This technique works even though the planetary system may be extraordinarily faint at visible wavelengths. The dead star becomes its own precision detector. Pulsar timing can respond to objects much lighter than the giant planets that dominated early searches around ordinary stars. It is one of the most remarkable examples of indirect discovery in astronomy. A hidden planet announces itself by changing the arrival time of pulsars that began beside an object barely wider than a city. The first confirmed exoplanets were found orbiting a rapidly spinning dead star. The breakthrough did not happen around a peaceful, sun-like star. In 1992, astronomers Alexander Wolskesen and Dale Frail reported planets orbiting the pulsar PSR B12 57+12. The discovery was astonishing because a pulsar is the compact remnant of a star that underwent a catastrophic supernova. Any original planets close to such an explosion would have faced extreme conditions. The newly identified worlds therefore raised an immediate question about their origin. Perhaps they survived in some form. Perhaps they assembled afterward from material surrounding the neutron star. Their existence proved something even more important. Planets were not unique to the solar system, and they could exist in environments that nobody would have chosen as the obvious place to look. Several of the pulsar's planets have masses comparable to terrestrial worlds. Their sky would be dominated not by a normal glowing sun, but by a tiny neutron star producing intense radiation. The first confirmed planetary system beyond ours was therefore stranger than most science fiction had prepared people to expect. Dead stars can retain planets or acquire entirely new planetary systems later. Stellar death does not always erase every trace of a planetary system. When a sun-like star ages into a red giant, it loses substantial mass before ending as a white dwarf. Outer planets can survive that transformation, although their orbits expand as the star's gravitational hold weakens. More massive stars may end far more violently and leave neutron stars behind. In either case, debris from disrupted companions or stellar material can sometimes settle into disks around the remnant. Under suitable conditions, that material could assemble into a new generation of bodies. Astronomers refer to this possibility as second-generation planet formation. Distinguishing survivors from later arrivals is difficult because both can inhabit the same ancient system. Their compositions and orbital arrangements may preserve clues to what happened. A planet around a stellar remnant therefore carries more than information about planetary formation. It can reveal the aftermath of stellar destruction. Some systems may contain worlds older than the dead star's final form. Others may contain bodies assembled from wreckage after the original architecture was transformed beyond recognition. White dwarfs may hide surviving planets beyond the wreckage of their former systems. A white dwarf is what remains after a star like the Sun exhausts its fuel and sheds its outer layers. Before reaching that state, the star expands enormously as a red giant. Inner planets can be swallowed or destroyed. Worlds farther out have a better chance of surviving. As the star loses mass, those survivors migrate outward because the weakened gravity can no longer hold them as tightly. Detecting such planets is difficult. White dwarfs are small and faint, while surviving planets may occupy broad orbits. Yet astronomers have found evidence that planetary systems can persist around these stellar remnants. A directly imaged giant planet has even been identified orbiting a white dwarf in an exceptionally wide path. These systems offer a glimpse of our own distant future. The Sun will eventually become a white dwarf, although that transformation lies billions of years ahead. By examining other dead stars today, astronomers can observe planetary futures that our solar system has not yet experienced. Hidden planets around white dwarfs are survivors from systems whose once familiar central stars have already completed their lives. Polluted white dwarfs reveal the chemical remains of planetary bodies they consumed. The atmosphere of a typical white dwarf should contain mostly the lightest elements because stronger gravity quickly pulls heavier material downward. Yet many white dwarfs show metals such as calcium, magnesium, and iron in their spectra. Those elements should not remain visible for long, which means fresh material must have arrived relatively recently. The leading explanation is planetary debris. Asteroids or fragments of larger bodies can be disturbed onto paths that carry them close to the white dwarf. Powerful tides tear them apart before the resulting material falls onto the star. By examining the chemical fingerprints left behind, astronomers can reconstruct the composition of destroyed objects that once belonged to another planetary system. Some resemble rocky material familiar from the inner solar system. Others show evidence of differentiated bodies with structures once divided into crust, mantle, and core. The star has effectively become a laboratory containing samples from planets we could never visit. A world may disappear completely as an intact object, yet its ingredients can remain measurable after being swallowed by the dead star it once orbited. Planetary debris around dead stars proves entire systems can survive stellar catastrophe. Astronomers have discovered compact disks of dust and rubble around numerous white dwarfs. These structures cannot be primordial material left untouched since the star was young. The violent red giant phase and subsequent evolution would have transformed the original inner system. Instead, the debris is thought to come from surviving planetary bodies that were later disturbed. A distant planet can gravitationally push an asteroid onto an elongated orbit. If that asteroid approaches the white dwarf too closely, tidal forces rip it apart. The fragments spread into a disk before some material eventually falls onto the star. This creates a chain of evidence. The debris tells astronomers that smaller planetary bodies survived stellar evolution. The mechanism that sent them inward may imply that larger planets survived as well. In other words, a ring of dust around a dead star can be evidence for an unseen architecture still operating farther out. The original planetary system may be shattered and rearranged, but gravity continues sculpting its remnants. Stellar death can end one version of a system without erasing planetary dynamics from the space around it. Brown dwarfs can host planets despite occupying the boundary between stars and planets. Brown dwarfs form more like stars than planets, but they are not massive enough to sustain ordinary hydrogen fusion in their cores. They occupy an intriguing territory between the smallest stars and giant planets. Astronomers have nevertheless found disks around young brown dwarfs that contain the raw material required for planet formation. Planetary companions have also been reported around these faint objects. Such systems push theories of planet building into environments containing far less mass than a Sun-like system. A small disk must somehow produce substantial bodies before its material disperses. The resulting planets can have unusual mass ratios compared with their hosts. From the surface of one of these worlds, the central brown dwarf would not shine like the sun. It would be cooler and dimmer, with much of its radiation emerging in infrared wavelengths. These systems also complicate terminology because the companion and host can approach one another in mass. Yet their existence demonstrates something profound. Planet formation is not restricted to conventional stars. Even objects that fail to become true stars can gather smaller worlds around themselves. Tiny red dwarf stars may conceal enormous populations of small rocky worlds. Red dwarfs are the smallest and most common true stars in the Milky Way. Their modest size gives planet hunters an important advantage. When a rocky planet crosses a small star, it blocks a larger fraction of the stellar disk than the same planet would block around the Sun. The star's low mass also means a small planet can produce a comparatively stronger gravitational pull. Surveys have consequently uncovered numerous compact systems around red dwarfs. Some contain several roughly Earth-sized worlds packed into regions much smaller than our inner solar system. Because these stars are so abundant and can survive for extraordinarily long periods, their planets may represent a major share of all rocky worlds in the galaxy. Yet many remain undiscovered because countless faint red dwarfs have not been monitored with sufficient precision. Their low luminosity makes them difficult to study at large distances. A star that appears insignificant in a survey could host an elaborate planetary system. If small planets occur frequently around red dwarfs, then some of the galaxy's greatest hidden planetary populations may orbit its faintest ordinary stars. Nearby stars could still possess undiscovered planets despite decades of astronomical observation. Proximity does not guarantee completeness. Many stars within only a few dozen light-years have been studied repeatedly, yet detecting every planet around them remains extraordinarily difficult. Small outer worlds can take years to produce recognizable patterns. Orbital orientation can prevent transits. Stellar activity can bury weak velocity signals. A cold planet might sit beyond the reach of present imaging sensitivity. Even a well-known star can therefore have an incomplete planetary inventory. This is why new instruments routinely return to nearby systems that astronomers have observed for generations. Closer stars offer better prospects for separating planets from stellar glare and measuring subtle motion, so previously hidden companions may become detectable as technology improves. The discovery of one planet can also motivate searches for additional worlds whose gravitational effects were too small to notice before. Our local stellar neighborhood is not a finished map. It is simply the region where the gaps are easiest to investigate. Somewhere among stars visible through backyard telescopes, entire planets could remain absent from our catalogues, despite having been practically next door throughout the history of modern astronomy. Proxima Centauri may contain additional worlds beyond the planets already reported there. The nearest star to the Sun has become one of the most closely watched planetary systems in astronomy. Proxima Centauri is a red dwarf, just over 4 light-years away. Proxima b was discovered through radial velocity measurements and has a mass broadly comparable to Earth. Additional signals have since produced evidence for other possible companions. Proxima d has been reported as a very low-mass inner planet, while a much more distant candidate called Proxima c has generated considerable debate. Different observing methods have not yet produced a simple picture of the outer system. That uncertainty makes Proxima especially fascinating. Even around our nearest stellar neighbor, determining exactly how many planets exist is difficult. Long-period signals require patience, and the star's activity complicates velocity measurements. Future observations may confirm additional worlds or remove some current candidates from the picture. Either result teaches astronomers about the limits of detection. The closest planetary system beyond our own remains partly unresolved. Distance is not the only barrier in exoplanet astronomy. Sometimes a star can be the nearest one in the universe and still keep part of its planetary family hidden. Alpha Centauri remains one of astronomy's most enticing places to hunt hidden planets. Alpha Centauri A and B form a nearby pair of Sun-like stars only a little farther away than Proxima. Their closeness makes them irresistible targets because any planets there would be among the nearest worlds outside our solar system. Yet the binary nature of the system makes precision searches challenging. Light from one star can contaminate measurements of the other. Their mutual orbit also produces large stellar motions that must be modeled carefully before tiny planetary effects can be isolated. Several intriguing signals have appeared over the years, but no secure planet has yet transformed either main star into a confirmed rich planetary system. Specialized imaging projects have searched for faint companions, while radial velocity programs continue pushing toward smaller masses. The scientific reward would be exceptional. A planet around either star would become a prime target for future atmospheric studies because of the system's proximity. Alpha Centauri therefore occupies an unusual position in astronomy. It is famous enough to appear in popular culture, and close enough to seem familiar, yet the most basic question about whether unseen planets circle its two bright stars remains open. Planet 9 could explain unusual orbital clustering beyond the known giant planets. Far beyond Neptune lies a population of small, icy bodies following extremely elongated paths around the Sun. Several of the most distant objects have orbital orientations that appear grouped rather than randomly distributed. One proposed explanation is the gravity of a massive unseen planet. Computer simulations show that a distant world several times more massive than Earth could shepherd certain objects into long-lived orbital arrangements resembling the observed clustering. The hypothetical planet would occupy an orbit vastly larger than Neptune's and would spend most of its time far from the Sun. Its gravitational influence could also help explain additional patterns among extreme trans-Neptunian objects. The case is not settled. The known sample remained small, and surveys are more likely to discover objects in some parts of the sky than others. That observational bias could create apparent clustering without requiring another planet. Researchers continue discovering distant bodies because every new orbit provides another test. Planet 9 therefore remains a hypothesis rather than a discovery. Its appeal comes from a clear scientific challenge. Something unusual may be shaping the remote solar system, and astronomers are trying to determine what. Searches for Planet 9 have already ruled out large regions of distant sky. Looking for a hypothetical planet does not mean scanning the heavens without guidance. Researchers use orbital models to estimate where Planet 9 could plausibly appear at different points along its proposed path. Telescope surveys then examine those regions for extremely faint objects moving slowly against background stars. Each unsuccessful search still provides useful information. If an instrument was sensitive enough to detect the predicted planet in a particular region, and nothing appeared, that combination of position and brightness can be excluded. Infrared surveys impose additional limits because a large, distant planet should emit some residual thermal radiation. Over time, these constraints shrink the space of viable possibilities. The search remains difficult because the planet could be exceptionally faint and positioned in crowded stellar fields. Its motion across the sky may also be subtle during short observing intervals. The process illustrates an important feature of scientific searches. Not finding something can still sharpen the hypothesis. With each well-designed survey, Planet 9 has fewer places and properties available in which to hide. If it exists, continued non-detections gradually force astronomers toward a narrower description of what it must be. If Planet 9 exists, one orbit may take thousands of Earth years. The proposed world would live so far from the Sun that its year could span a substantial fraction of recorded human history. Estimates depend on the exact orbit, which remains hypothetical, but periods of several thousand to more than 10,000 Earth years are plausible in many models. Such a planet would move extraordinarily slowly when compared with the familiar planets visible from Earth. Human civilization could rise and transform while the world completed only part of a single revolution. Its distance would also vary greatly if the orbit were strongly elongated. At its farthest point, sunlight could be reduced to a tiny fraction of what reaches Earth. That long period helps explain why direct detection is difficult. Astronomers cannot wait to observe anything resembling a complete orbit. They must identify a faint point and then measure enough motion to show that it belongs to the solar system. If Planet 9 is eventually found, its orbit will largely be reconstructed through mathematics rather than watched in full. Humanity could discover the planet without any person ever seeing it complete even 1 year. Hidden planets could preserve ancient evidence from the birth of planetary systems. Planets that remain far from their stars can retain materials that were altered or lost closer in. Lower temperatures allow volatile compounds to survive more readily. Their atmospheres and interiors may also experience less intense irradiation. This makes distant worlds valuable records of the environments in which planetary systems formed. Giant planets are especially important because their bulk composition contains clues about where they assembled inside the original disk. Ratios of elements can reveal whether a planet formed beyond particular condensation boundaries before migrating elsewhere. Orbital arrangements provide another historical record. A planet on an eccentric or highly tilted path may preserve evidence of ancient scattering events. Resonances can reveal past migration through the disk. Even a rogue planet contains history because its composition may identify the kind of region from which it was expelled. Hidden worlds are therefore not merely missing pieces in a census. They are archives. Discovering one can provide evidence about events that occurred billions of years before any telescope existed. The farther astronomy pushes into overlooked planetary populations, the more completely it can reconstruct how planetary systems became the architectures we observe today. Every detection method reveals a different slice of the galaxy's planetary population. Transit surveys excel at worlds whose orbits line up with Earth. Radial velocity measurements respond strongly to massive planets that tug noticeably on their stars. Direct imaging favors luminous young companions with wide separations. Microlensing reaches cold planets and free-floating objects through chance geometry. Astrometry measures motion across the sky and becomes especially useful for certain longer-period companions. Pulsar timing can detect extraordinarily small gravitational influences around neutron stars. None of these methods samples planetary space evenly. Their strengths overlap in some regions and leave substantial gaps in others. This means astronomers learn the most when techniques are combined rather than treated as competing approaches. A planet discovered through one method may become measurable through another, allowing size and mass to be determined together. Population studies also become stronger when biases from separate surveys are compared. The galaxy itself has no preferred detection method. Only observers do. To understand what kinds of planets truly exist, astronomy must piece together partial views produced by instruments that each see a different version of the same enormous planetary population. The planets we know may represent only the easiest fraction to discover. The modern exoplanet catalogue is one of astronomy's great achievements, yet it should never be mistaken for a complete inventory. Every listed world crossed a threshold that countless others did not. It was large enough, close enough, warm enough, properly aligned, or gravitationally influential enough for a particular observing technique. Planets that fail those tests can remain absent from our records even when they are physically common. This creates a strange situation. Humanity has moved from knowing only the planets around the Sun to recognizing thousands around other stars, while still understanding that the majority could be missing. Statistical corrections help estimate unseen populations, but those estimates become least certain precisely where observations are weakest. Future telescopes will push the boundaries towards smaller and colder worlds. Some discoveries will probably reveal types of planetary architecture that current catalogues barely contain. The known planets are therefore both a treasure and a warning. They show how varied nature can be, but they also show what our technology has happened to notice first. The unseen portion may prove even more diverse. The Milky Way could contain trillions of worlds still waiting to be found. The galaxy contains hundreds of billions of stars, and planet surveys have shown that planets are common around them. Many stars host more than one world. Add the possibility of free-floating planets, and the total rises further. Depending on how frequently small rogue worlds occur, the number of planetary mass objects in the Milky Way could reach into the trillions. Most will never receive individual names. Many may never be detected at all because they are too distant or too faint for any foreseeable telescope. Yet each one is a physical place with its own history. Some circle stars that will shine for trillions of years. Others move through interstellar space without a sun. Entire categories may remain poorly represented in present catalogues because our methods favor only certain masses and orbits. This scale changes the meaning of planetary discovery. Finding another world is no longer evidence that planets exist elsewhere. We already know they do. The deeper question is how many forms they take. Every new detection is a tiny opening into a population so enormous that humanity has only begun to comprehend it. And so, we come to the end of our journey through the hidden planets of the universe. We have seen how entire worlds can remain invisible, even when they are relatively close by. Some reveal themselves through the motion of a star. Others are discovered through fleeting changes in light. And some may travel through the galaxy without a sun at all. We have followed planets into distant systems, around dead stars, and far beyond the regions that our telescopes can easily search. We have seen how a missing world can leave clues in the orbit of another planet, or in the shape of a dusty disk around a young star. And perhaps the most remarkable thought is that the planets we know may be only a small part of what is really out there. Beyond the reach of our current instruments, there may be cold worlds circling distant suns. There may be rocky planets moving through interstellar space. There may even be undiscovered worlds much closer to home. But for now, there is nothing left to search for. You can let those distant worlds continue on their journeys without you. Let the stars drift farther into the background. Let the questions become softer and allow your thoughts to loosen their grip. Notice the weight of your body where you are resting. Let your breathing settle into its own rhythm. There is nowhere else you need to be, and nothing else you need to solve tonight. If you enjoyed this journey, you are always welcome to like, subscribe, or leave a thought below. And if you happen to still be awake, there is another video waiting for you on the screen. You can continue exploring, or simply let it play as you drift towards sleep. For now, let everything become still. Sleep well and good night.